Okay, let's get started. Faraz, let me know when you're recording. You're recording, great. Okay, hi, welcome to the third Egocentric Research tutorial with Project Aria. I'm James Ford, and I'm a research product manager at Meta Reality Labs, and I'm privileged to work with some of the world's leading engineers and researchers in the areas of AR, VR, SLAM, and 3D vision, both in Meta Reality Labs research, which you'll be hearing from today, and amongst our academic and commercial partner base, many of whom are here today. And I'm glad to see you all here. I'll just start by asking a quick question. Who saw the Orion announcement at Meta Connect recently? Can I get a show of hands? Great, yeah. And how many of you have worn a pair of Ray-Ban Meta glasses? About a quarter of people in the room, great. And how many have worn a pair of Aria glasses? Great. It's clear that Meta is investing significantly in smart glasses, and today we're going to talk about the kinds of research that are possible with Aria in the areas of contextual AI and what's going to enable the future of smart glasses. So we've got a really packed agenda. First, we'll talk about Project Aria for human-centric AI and share some exciting updates in the tools and resources that we provide to you as researchers. And then we'll take a deep dive into the new digital twin catalog that we're releasing for object reconstruction research. Zhao's going to talk about that. We'll walk through recent data sets that our organization has worked on for helping to understand things like where we are in space and what is in the space around us and how we interact with what's in the space around us. And these are kind of the central problems to augmented reality and contextual AI. So we'll hear from Prithviraj, who's going to talk about hot 3D data set for hand-object interaction. And we'll hear from Lingni, who's going to talk about Nymeria, which is a human pose estimation data set. And then Julian's going to talk about egocentric foundation models. And these will cover these areas that I just described. And then we're going to hear about the now famous and highly cited Ego EXO40 data set from the Ego40 consortium. And I'm very excited to have three external researchers in our partner community who are going to talk about data sets that they are now creating using Aria. And I think we're in an era where we're seeing a real proliferation of egocentric data sets with Aria. And I'm really excited about that. So I'm going to start things off here with a discussion of human-centric AI. And I'm going to give an overview of Project Aria. And then Xiaqing and Yang here are going to show some live demos that will give you an idea of some of the tools that we have. And we'll break up the session a little bit with these live demos. Okay, so many of us here are working towards a future where AI systems can provide the right information exactly when we need it. Imagine a true personal assistant able to help you in any complex task, able to give you reminders in the moment based on your context. AI is here today, but it's not the vision that we described just yet. How many of you use a chat-based LLM more than you use a search engine now? It's actually an interesting mix of results. I think if I asked that question 6 months ago, you might have a different answer, actually. And I think I've hit the turning point pretty recently, and there's a reason that that turning point is happening, and it has to do with context window and the ability for these LLMs to provide information that represents more of the information that is around us. But we can all tell that chat interfaces with language models are limited in a major way. AI systems are only going to be as good as the training data that are used to create them and the context we're able to provide to them when we ask them for things. So I'm going to dive into these areas. Let's talk about training data first. LLMs are primarily trained on internet data, which is mostly text and images, and they make meaning of the world from the patterns inherent in those data. But our lives are much richer than text and image data on the internet, and it's impossible for these models to know about us without us supplying some form of contextual information. So what exactly do I mean by context or contextual information? Well, when we're talking about a chat-based LLM, we're talking about typing in text into an interface what we understand about a day or a month, and really codifying that with language in this really condensed way that has a high cognitive load to condense and is lossy in so many different ways. It's such a small signal, and we need to reach into our memory to formulate phrases that capture an entire day. For AI to be truly useful to us throughout our daily lives, it needs to be trained and operated from the human perspective. This means we need to train models with data that capture as much of the human perspective as possible. And it means we need to utilize sensors that perceive from the human perspective at the time of inference to provide those signals. And that's really the overarching goal that we talk about with egocentric or human-centric AI. Let's just take a look at what this human perspective looks like. It's much richer than a network of text and images. As humans, we walk through environments, we look at objects, we hold objects, we interact with people in the environment, and we engage in complex mental and physical tasks like cooking a recipe, assembling furniture, or learning a new sport. How can we possibly capture such a variety of experiences? Imagine trying to hold your phone the entire day to capture your day. It's just not practical. Or imagine wearing an AR headset all day. That's also not practical for some obvious reasons like weight. So we need a device to collect human-centric data to do this kind of research. And it needs to optimize for two things. One, it needs a set of sensors that can collect data on the order of what a human can sense. And then it needs to be in a form factor that can actually be worn all day. So devices like HoloLens or Quest have the sensor suite that we're talking about, but they're too heavy and bulky to wear for long durations of time. And then on the other axis, devices like the Vuzix glasses or GoPro camera can be worn all day, but they lack the kinds of sensors that are needed for this kind of multimodal perception of the world. So we realized that to move egocentric research forward, we needed to create an entirely new device for this kind of capture. And that's why we came up with the Aria glasses with Project Aria back in 2020. And I don't want anybody to mistake this. This isn't Orion or Ray-Ban Meta. We can definitely distinguish this as a research vehicle and not a prototype of a product or a product that we sell today. It's a tool that we use extensively in our own research and that our academic and commercial research partners across the world have been using for several years now. So let's dive into what Project Aria is specifically. It has an RGB camera, SLAM cameras, eye tracking cameras, IMUs, spatialized microphones, and various connectivity options. And that's essentially all the input mechanisms you'd expect on an AR device or future smart glasses. We use Project Aria internally for many of our research efforts, and we also make Project Aria available to you as researchers. We give Aria glasses to limited partners, and we provide the Aria Research Kit, which is a supporting kit of tools and AR-centric algorithms. We also have the open science initiatives where we release datasets, models, and tools to support community users who don't need to have the devices in hand. And I'm going to give you an overview of what each of these are, and then show some things in each of these areas that are new to you. So let's start with Aria Research Kit and walk through an overview. I'm going to talk through some ways of using ARK and discuss some new capabilities. Okay, if you want to do egocentric research, you not only need a device like Project Aria glasses, you also need tools to configure and manage this massive amount of rich data, ways to process the recorded data and extract contextual meaning from it, such as where the wearer's eyes were at the time of recording, what they were looking at, and what their hands were doing. And even ways to develop applications that could, for example, run inference models directly on the live data streams. We're actually going to see a demonstration of that right now, and we're initializing it as we speak. You can see Xiaqing doing that. So ARC will enable you to record, process, prototype, and efficiently consume egocentric data for all sorts of downstream tasks, processes, and we'll look into some of these. So probably the most obvious thing that you can do with the Aria glasses is record data. It's a recording device, and let's talk exactly about what that means. On the Aria glasses, which Xiaqing is holding right now, there's a button on the top right, and that button allows you to start and stop a recording. And you can record easily for a few hours in the wild. In fact, if you use a battery pack, you can record even longer. And then you're really only limited by what can fit on the hard drive on the device. We believe in building a responsible future for Project Aria. And I'm just going to briefly explain that what we're doing right now is creating a map live as part of a demo that we'll show you in just a moment. And just by moving around the device, we're using the sensors to feed into a real-time running SLAM system. We're going to show you that in just a little bit. We believe in building a responsible future for Project Aria, and we put premium on privacy. We have community guidelines where all of our partners agree to record only in consented environments. And additionally, we have an obvious LED, which you can see as a white light on the front of the glasses. And that lets everybody know in your consented environment that you're recording. And there's also a privacy switch, which enables you to immediately stop and delete a recording if there's any privacy concern. For example, if somebody walks by and they weren't really part of the experiment you were trying to run or the data you were trying to collect, you can easily hit the privacy switch and kill the recording. So not only do we allow you to record with the buttons that we showed you on the device, we also make it really easy for you to configure and manage your recordings out in the world with a mobile companion app that runs on both Android and on iOS. And you can think of the companion app like a remote control for the Aria glasses. So let's just take an application like OCR, optical character recognition, which depends most heavily on eye tracking camera and the RGB camera. That's very different from something like a scene reconstruction task that would depend much more heavily on the SLAM and RGB camera at high frame rate. You could easily optimize your sensor configuration for your application directly in the companion app when you're out in the field by selecting a pre-made profile in the companion app. These profiles essentially specify which sensors you want to use at which frame rate when you're recording. And if one of those profiles is not optimal for your particular task, we offer a custom profile option, which allows you to pick exactly which sensors at which frame rate you want to utilize. And we now have features, if you look all the way on the right, that enable a live preview of the visual sensor stream. So this means you can have confidence in your recording when you are out in the field and you're not quite sure what the glasses are looking at. We're just trying to make it as easy as possible for you to do as much as you can out in the field with these features on the companion app. A growing topic in the egocentric research community is multi-view research. And we have the idea that, for example, a soccer match could be reconstructed from multiple simultaneous wearers in an audience. And we've recently added features to enable multiple glasses to be time synchronized in the range of millisecond accuracy using an algorithm called tick sync. And you can see with and without tick sync in the video above. The top frame shows essentially no time alignment, and the bottom frame showed a very time-aligned result. I can show that again, just briefly here. Yeah, if you look at the bottom, you can see multiple views of the same video footage, perfectly time-aligned. So now you can imagine cases where you could have 4 or 5 pairs of glasses. I've even seen 7 running at the exact same time in time sync. So in order to make use of egocentric recordings, you need more than just the raw data. You need the same kind of information that an AR system computes in real time to understand how the wearer is interacting with the world around them. So we'll talk about processing. So because Meta invests so much in AR systems, we have state-of-the-art algorithms for things like SLAM, simultaneous mapping and localization, eye tracking, and hand tracking, and we want to make all these available to you as researchers. Some of those algorithms are our core IP. And the way that we make these available to you is that we have a cloud service called Machine Perception Services, which essentially houses these algorithms and allows you to upload the algorithm, upload your data, your recordings, and have those processed by these algorithms. But your data is always yours. The reason that we have this cloud system is that we're trying to protect our IP, not take your data. Your data is always yours in these cases. So let's just jump into one of these results. This is our per sequence pose estimation, leveraging a proprietary visual inertial SLAM system that's built specifically for Meta's products. It combines a VIO front end with a large scale capable mapping back end. And it's meant to work everywhere and always with some limitations. But we highly encourage you to take it out of the lab. As you can see here, this is walking around areas like city blocks, whole outdoor scenes, inside of buildings. And one of the things I want to call out is that this is stable for long trajectories. It's meant to work over long distances. So what exactly do I mean by large scale or long distances? Here we can see an example of a whole city block in Seattle being mapped with the SLAM system that we have. And you can see a round trip around this block. And what I think is actually most compelling about this kind of result is if you look up, you can see just how high it vertically maps and with a very high resolution on feature detail. But you don't have to create a map alone or in one shot. We're working towards this vision where we can have live maps that are always updated. And those maps are going to have to be formed over time. This is an example where we see multiple recordings taken at different times, showing multiple trajectories within a building, all computing one shared map. And this is a solution that we have called multi-SLAM. So SLAM will compute a map that's useful for tracking and localization, and it's really meant to be optimized for that purpose. And it's also possible to take those kinds of algorithms and compute a very dense and rich point cloud that you can use as a visualization of your space. Or you could also use that to construct downstream representations of the space, like a mesh, for example. And we make these point clouds available via the machine perception services that compute SLAM. It puts things in a much more visual context. And what you can actually see here is the trajectory moving around as the point cloud is being rendered. Okay, so those are kind of our space-centric algorithms. We also have what I'll call human-centric algorithms. And the first of these is our eye tracking algorithm. So imagine you want to perform optical character recognition. Our eye gaze model utilizes the eye tracking cameras that are on the glasses, and it projects an eye gaze vector with depth estimation in 3D. So the purple vector that you see on the left is the eye gaze direction from each eye computed, and we have a distance that's computed as the intersection of the vector coming from each eye. So we have a depth estimation here. And you can see the blue dot on the right, and that right image is a reprojection of that vector from 3D space back onto the 2D image. So we enable you to get the point specifically for your eye gaze directly on the 2D RGB images, which you can imagine is enormously valuable for OCR tasks and anything else where you're trying to assess the eye gaze. Another thing I want to call out really quickly is we enable you to perform a per session eye gaze calibration following a guided process in the companion app. And that enables you to have very highly accurate eye gaze directly in your session. And then we also have a service that predicts the wrist and palm key points, along with normal vectors that allow the orientation of the hands to be represented. And as you see here, you can see the wrist and palm positions reprojected into the RGB frame. So this gives you the orientation as well as the position of the hand. And we actually, under the hood, compute 21 key points to have full articulate understanding of all the hand joints. But again, because that's our IP, we can't expose all of that. And we give you this abstraction, which is the wrist and palm key points. But we also want to make it really easy for you to, additionally, if you want to, take a third-party model like MediaPipe and project it onto the wrist and palm key points. And in that way, you can have a full fidelity output from the hand tracking algorithms that we utilize. Okay. So here's something new that you might be excited about. Aria excels at enabling computer vision from a 3D perspective. And we put a lot of work over the past months to make our RGB camera calibration extremely accurate for all your downstream tasks that utilize the RGB camera. And we've drastically improved how well we can temporally and spatially register RGB images, often down to pixel level accuracy. So I'll give you a visual of what this looks like. Here we've got a couple of objects. You may have seen this earlier from Hot 3D if you're in the other workshop. But what we have here is a representation of these objects in 3D space, reprojected back into the 2D image. And you can see this toggling between a view that utilizes an RGB online calibration and before RGB online calibration. With RGB online calibration, which we've just released through our machine perception services, you can see an extremely accurate pixel-wise reprojection of the 3D back onto the 2D RGB image. And this is really useful for downstream tasks that leverage this signal. Let's take an example of a downstream task that needs a really high accuracy RGB online calibration. So this is a Gaussian splat reconstruction of a scene that we've done. This is actually, I believe, in Menlo Park. If you look on the left and the right, what you see is the factory calibration and then the result of online calibration. And you can see this yellow band swiping left and right, almost like a squeegee cleaning the surface. And you can see the text, this like R and all of these symbols on the window getting drastically clearer as you go from left to right. And that may seem relatively subtle if you're looking at an image like this, but when you're talking about doing research for an immersive experience in something like a VR or AR scenario, these kinds of details make a massive difference in the level of immersion. And without this kind of solution, you can imagine it breaking immersion for the user. So RGB online calibration is actually enormously important for enabling really high quality 3D vision tasks. So how do you access machine perception services? Well, we've got a couple of ways. We've got Aria Studio, which is a desktop application, and we've got a command line interface, which is a more programmatic application. And for those of you that are still using the Aria desktop app, actually, I just want to take this opportunity for the Aria users that are out in the crowd. Have you seen Aria Studio yet? Can I just get a show of hands? A few people. And then who's still using the desktop app? Anybody using the desktop app? A couple people. Okay. I know there are some reasons. For example, we don't have Windows support right now for Aria Studio. But for those of you that are still using the desktop app, I highly encourage you to download Aria Studio. And you can do it with a simple pip install. It's available in the documentation. And this is going to drastically improve your experience in a number of ways. Number one, it's a way better UI than the desktop app. It's going to get updated way more frequently. It's very easy to download. And let's just dive into it a little bit. I'll show you a brief just run through of a video here of Aria Studio. So the first thing that you're going to see is a login. And once you log in, you can see that you can access your recordings. You can manage your machine perception service jobs. Here I have multiple VRS files that are on my glasses. And I can transfer these very easily to my local machine. And these transfer quickly and I get a real-time update. And then I see them on my local machine. And then I can select which ones I want to send for processing. And I can choose, for example, SLAM, eye tracking, hand tracking. And not only can I choose these, but once I've submitted them, I can get a very quick glance of what the status of the job is. And then I can take that down. And once I actually have my NPS results, I can easily open up the NPS results in a visualizer, and I can see them in 3D. And we're going to see just what viewing them looks like right here. And this opens up Rerun Visualizer, which we'll also look at in a demo in just a moment. And this is a really high quality 3D visual of our recording and our NPS results. Okay, so I just highly recommend that you move to Studio if you're still using the desktop app. Another thing that you can do is you can run the NPS CLI, which is a more programmatic and batch-oriented way to process your NPS jobs. And this is an example of just some simple command line interfaces to start the CLI. And then you'll see just a brief walkthrough of the interface. Okay, so we're going to log in, and then we'll be able to quickly view the process of some jobs here. I'm just going to skip ahead a little bit on this video. So I can see the status of jobs. I can see that some are computing eye gaze and some are computing SLAM. And this, again, is great for batch processing and programmatic access. Okay, so we talked so far about recording, and then we went a little bit into processing. We have all of these algorithms that we're computing. I actually want to just jump into a live demo where we're going to show you some of these algorithms working live on an actual machine, and we'll talk through some things. All right, Xiaqing's going to show me some recorded signals from these glasses that I'm going to wear. We're a little space constrained. Bear with us. I'm going to have to turn around this way.
Yeah. All right, thanks, James. Yeah. So I'm going to show you the Aria demo here. So this demo shows you two important capabilities. The first one is how we stream the Aria raw sensor data from the Aria glasses to the PC. The second one is how we run a bunch of machine perception algorithm on the PC in the real time. Okay, let's see the first one. So I want to draw your attention to the raw data of the Aria glasses. At the left bottom, what you see is two slant camera of the Aria and see how wide field of view of it. And on the right of it, that is the eye tracking raw sensor data showing James' eye, which is moving. At the right top, that is RGB raw sensor data of the Aria. That probably is one of the sensor data you're interested with the most. In addition to the raw sensor data, the second thing I want to show you is three NPS capabilities that we run on this PC. The first one is that if you look at the left top, that shows how 6 dot pulse of the Aria glasses is computed in real time. That little fluster that is moving when James is moving, right? That the second thing is the semi-dense point cloud. That is also computed in the real time. You probably see the speaking stand there, and also the table. Table is aligned. There is a, it's facing this way. To be. Next to the SLAM result, what we want to show you is the eye tracking result. If you look at the top right, that small blue box, that is the eye gaze that is computed in the 3D and reprojected into the 2D RGB. That shows what James is paying attention to in this RGB image. And the size of the blue box shows the uncertainty of the eye gaze prediction. Next is the hand tracking. And James, if you raise up your hand, you see these key points of his hand, which is also computed in the 3D and reprojected onto 2D, showing the hand is tracked using the Aria sensor data. One more thing that I want to show you is the capability that you can also integrate any open source model with the Aria raw sensor data. At the lower right, what we show here is an open source object detector that is integrated with the Aria. We use static for this demo. This bounding box shows how the object is detected in the field of view. In the next, James, would you like to play the game with me? We played the game thousands of times in our lab, which is called fingertip tracking. Now I'm moving my fingertip, and James used his eye to track my fingertip. And what I want you to look at is the top right. That small blue box is following my fingertip. All right, that's all for demo, and I'll give the stage back to James.
Thanks, Xiaqing. Cool. What I want to re-emphasize is what you saw there was these algorithms running live. Those algorithms, again, those are available via the machine perception services. We just wanted to give you as clear as possible of a demonstration of what those algorithms do in real time. And additionally, that's the SDK. that you can use. So what I mean by that is the streams of data that are coming out of the raw images, you can also stream those with our SDK and develop any kind of application that you want from that result. Okay, it looks like back up on the screen. Great. Okay. So now let's talk about one more use case, which is how we consume that data. So we've done our recordings. We have computed results with machine perception services. Let's say we want to create a data set, a novel data set with Aria from an egocentric perspective for some task. We probably want to prepare our data set in some very specific ways. And we've got some great tools for actually working with the data. This is a very lightweight VRS player that we've just made available. And this is part of what we're calling VRS peripheral support. This lightweight VRS player enables us to, with just a single command, open up a VRS file, take a look at it. And in this example, what we're going to do is we're going to find a very specific point in time where we want to trim the VRS file. So let's say you've used, for example, eye calibration at the beginning of your recording and you want to trim that out from your file. Here we found a very specific time and we've trimmed out the part of the recording that has the eye calibration in the beginning. This makes it very easy to start to work with VRS data. In this other example, let's say we now want to get rid of some of the raw sensor streams, for example, the eye cameras. You can imagine, for example, that you use the eye tracking cameras in the very beginning of your process to compute the eye gaze. But then once you're done with that, if you want to publish your data set, you don't want it to be a bloated data set with unnecessary data streams. You can imagine removing the eye gaze. And here we have an example of using this tool to select the eye gaze specifically using an ID, and then very easily copying it to another file and removing sorry, that's the second video. In the second video, we can see, I'm just going to jump ahead a little bit. We identify the stream that has the eye gaze via an ID, and then we copy to a new file that removes that stream. This one's called noeye.vrs. We remove the 211 stream. Okay. So I showed the lightweight viewer, how to work with VRS files. Of course, there's also the rerun-based viewer. This is both a C++ and Python-based visualizer, and it's based on an open visualization library. And this is where you can really dive deep and develop 3D visualization of your process data once you've computed SLAM and have a 3D representation from your recordings. So this is just an example where we have many different signals, both being shown in the 3D space and in the 2D projection at once. And if you want to work more interactively with your data, we offer a Colab notebook with visualizers and data loaders, and you can work very interactively in that sense. Okay, that was the Aria Research Kit. I'm just going to briefly give you an overview again. You can record with the Aria glasses, then you can process data with algorithms that we have, and we make those available via the machine perception services. And then once you've processed things, you might want to even look at developing prototypes. You can do that with the SDK. You can stream data with the SDK. And then if you're doing something like preparing a data set, you can then process that data using VRS tools that we have and Project Aria tools. And that's for consuming data. So now let's jump a little bit to, let's say you're not quite ready to start recording with the Aria glasses and you're still trying to get used to egocentric data. Really, the easiest way to get started is via the open science initiatives. And we realize there's a time investment involved in getting used to egocentric data. So we want to provide you with immediate resources to enter into using egocentric data. And those are essentially models and data sets that we make available to you. So let's just start by talking about models. One model that we make available is called EgoBlur. And it's really important that we realize that we're trying to create a future where we are doing things like collecting in consented environments and protecting PII. And so in this sense, we offer an EgoBlur model, which does both blurring of faces and license plates. And we offer this model to you so that you can prepare your data sets in a way that protects personal information. And then we have data sets. And the number of data sets that we have is really growing exponentially. We focus on research to solve core problems around understanding our environment, again, where we are in the environment and how we interact with the environment. So we're going to hear from Zhao and Julian and Lingni and Prithviraj a little bit later, and we're going to dive deep into 4 of these data sets. But I'll just briefly describe that Nymeria in the top left provides you with rich data for human motion estimation. Aria Digital Twin in the middle builds the perfect digital replica of a real physical space and allows you to do various egocentric tasks in that space, like object detection and activity recognition. And then on the top right, we have Aria Synthetic Environments, which provides 100,000 synthetic room layouts for various scene-oriented tasks. Hot 3D, which you may have heard about this morning in the bottom left, is a hand-object interaction research data set. Prithviraj is going to talk more about that. And Aria Everyday Activities showcases multiple applications from egocentric data like scene reconstruction. But now I want to introduce the new digital twin catalog, which we're announcing today. And Zhao is going to dive into some detail, but I'm just going to kick it off with a video that we have describing this data set.
The ability to easily create and manipulate digital 3D representations of objects from the real world is integral to immersive experiences in many applications. E-commerce is just one example. This is where digital twins come in. These are highly accurate digital representations of physical objects that are indistinguishable from their real-world counterparts. Digital twins used for immersive applications today often have to be crafted by technical artists. There's a high skill and cost barrier. Making robust 3D reconstruction easier to accomplish is the most important step that the computer vision community can take towards the democratization of digital twin creation. At Meta Reality Labs Research, we've made a major investment to bridge this data gap with the release of the Digital Twin Catalog. This is the world's largest and highest quality 3D object model dataset for 3D reconstruction research. The Digital Twin Catalog is a large and highly detailed set of over 2,400 common, everyday 3D models of real physical objects. They are accurate to a sub-millimeter level and photorealistic. The dataset also contains recordings of these objects from cameras and from the Project Aria smart classes to enable dense and sparse view reconstruction research. You can find the Digital Twin Catalog on the Project Aria website. Here, you can download the dataset to get familiar with the data and begin improving your reconstruction algorithms today.
So I encourage you to download that dataset and start experimenting with it right away. Another thing that I want to call out for those of you that are familiar with the Aria Digital Twin dataset is that there were a bunch of objects that were utilized in that dataset that are now also available via the Digital Twin Catalog. So for those of you that have worked with that data set and want to perform further tasks like object detection, please download the DTC data set and get those additional objects. And then coming soon, I just want to announce that we're going to have an academic object reconstruction challenge in partnership with Shopify. And there will be over 7,000 additional objects that we'll make available from Shopify's merchants. And one of these is named Our House, and you can see some of these extremely high quality 3D objects that are on the right. And so stay tuned for more information about when that academic challenge will start, how it's going to work, etc. And we'll tell you more about that shortly. Okay, another new item that I want to talk about is Aria Training and Evaluation Kit. And the high-level takeaway here is that if you've worked with Aria data, it is not the most straightforward type of data to use for machine learning purposes. And we've recognized some of the challenges around that. And now we're making it order of magnitude easier for you to work with Aria data for downstream tasks like training in PyTorch. So consider that before, if you're working with VRS data, which comes from Aria, it's a format that was developed for multimodal applications. And we're now providing ways that you can take that VRS data and with just a few easy API commands, you can prepare data for training. And before, this would have taken perhaps weeks or months to write manual pipelines. So I'm excited to have Yang give us a demo here in just a moment. Another couple things that I want to just mention is that we have pre-processed a bunch of this data already. And so for two major data sets, that's Aria Digital Twin and for Aria Synthetic Environments, we've already prepared this data ready in PyTorch format. This would be like the easiest possible entry point for you to work with egocentric data for training purposes. We'll support more coming soon. And then another thing is we want to make sure that we understand as a community what kinds of models work well with egocentric data. And from that perspective, we've developed a standardized evaluation library that has unified file formats and rich APIs. And right now it supports two ML tasks, that's 3D object detection and surface reconstruction. We're shortly going to have a leaderboard. And the whole idea here is we want to come together as a community to start to evaluate different models for egocentric research. Okay, now without further ado, I'm going to hand things off to Yang, who's going to do a demo of the Aria Training and Evaluation Kit.
Yeah, thanks, James, for the introduction. So my name is Yang, so I'll be our tour guide for ATEK today. I'll show three demos here. One for data pre-processing, one for model inference, and one for model training. So let's just jump right in. So for the first demo, we will show how to pre-process an Aria data sequence. We'll take Aria Digital Twin as an example, and we'll work on a 3D object detection task and with an example model called QRCNN. So let me run some setup here. There we go. Okay. So the user will start with this ADT sequence. It contains the Aria reporting in VRS format and a trajectory file in CSV and some object annotation files in CSV or JSON. And on the other hand, the machine learning model QRCNN, it expects synchronized data frames consisting of image, calibration, annotation, and poses. So to go from the input data to what the model requires before ATEK, the user would need to implement all of these following steps by themselves. So the key question is, how do you do everything correctly and make sure that the generated results across all these data are consistent, including image, including bounding boxes. So this is cumbersome, this is non-trivial for everyone. So what we did is that we built this ATEK library where we handle all the implementation details for you and simplifies your work just down to a configurable YAML file. So let's take a look. So this is an example configurable configuration YAML file. So the user can just pick the data that you want to include in your pre-processing. In this case, we have RGB data selected as true. And we also select the trajectory data, which contains a pose. And also here we select the object bounding box data. So, and also the user can also control the how you want to do image processing by choosing the options here. So in this way, you can just craft your own pre-processing configuration, just a YAML file. And then once you get your YAML file ready, and then you can just call this API, just one line, to create an ATEK preprocessor and call process all samples to go through the entire sequence. So let's just run that. Visualization show this screen. Yeah. So this is a visualization of the pre-processed data. So the user can use this visualization to verify that the pre-processing is done correctly. For example, if you look at the bottom, you can see that the annotation and sensor data, they're synchronized in time. And on the in this image, you can see that I have rotated my image to the upright position, and also I have make my camera model linear. You can see the straight line here. So now let's take a closer look at what's the actual content of the preprocessed results. So let's print this. So this is the content of the results. So we can see that we have converted the input of VRS plus CSV plus JSONs into Python dictionaries of tensors, strings, or sub-dictionaries. So this is more convenient because this can be directly fed into PyTorch workflows. And also in ATEK library, we write the preprocessed results onto local disk in a web data set or WDS format for future use. So this is it for demo 1. So we have shown how you can preprocess an Aria data sequence. And now let's move on to model inference. So before we jump into model inference, I want to introduce this convenient feature called ATEK data store. So to preprocess a large data set is time and resource consuming. So for example, it takes 14 days to preprocess 10,000 Aria sequences without parallel computing. So to address this issue for the user, we built this data store where we host preprocessed Aria data sets for user to access. You would have 2 options here. So you can either download the data to your local computer, or you can actually stream the preprocessed data over the internet. So you can simply go to projectaria.com, and you can pick the data set here, and if you see a button called something in ATEK format, it means that we have preprocessed this data for you. You can download the PyTorch ready data set. Okay. So I was planning to show a streaming demo, but due to the internet speed of the conference, I'll show a local download version instead. But we promise you the streaming feature will be working once you have a better internet connection. Here is how you can generate some streamable YAML files. And then you can use this API to load your YAML file and use this API to create a PyTorch data loader from your preprocessed data. So the PyTorch data loader would just produce data samples in ATEK format dictionaries. And to further fit the ATEK format dictionary into your own model, in this case, QRCNN, we'll need to write some kind of data transform function. We'll need to do some dictionary keyword mapping. We need to reshape some tensors or reorder some tensors, plus some other data transformation operations. So in ATEK, we provided several example data transform functions for different models. You can follow our guide here and our example here too when you're writing your own data transform function. So once the data transform function is integrated into our API here, so the created PyTorch data loader now directly returns data sample in the model specified format. So for example, you can see that this dictionary is now in the QRCNN convention. So once you have the data, PyTorch data loader, running inference is very easy. You just load up between model, and then you loop through your created PyTorch data loader, and you just do your normal inference step. So this is very easy. So let me just run this for a few batches. And then we can visualize the QRCNN inference results. So here we're plotting the bounding boxes, the 2D and 3D bounding boxes, where the green one is ground truth and the red one is prediction. Okay. So once you have the inference results, the next natural question is how do I quantify my model performance? So in ATEK, we provided a standardized evaluation library, as James mentioned, for each machine learning task that we support. So we include standardized prediction file formats. We implemented some common evaluation metrics for the user, and we also include a simple benchmarking script for each task. So, for example, here is the prediction file format for the object detection task. what the user needs to do is just to parse your model output into the prediction file format, just like this. And then you can run our benchmarking script to report the evaluation metrics. For example, here for detection, we're reporting MAP, we're reporting average precision, average recall. We also report the MAP for each object category. Okay, so this is all for the second inference demo. Now let's move on to training. Okay, model training. So in model training, you can still leverage ATEK data store to download the pre-processed data for training. Here, I'm showing the command for downloading data from our data store, but I also actually skipped the downloading part. So specifically for training, ATEK included an example training script for this Q-bar CNN model. The core code is included here. So actually, it's just essentially 2 lines. You load the YAML file, either from ATEK data store or from your local computer, and then you can call the exact same API as I have shown in the inference to create a PyTorch data loader specifically for your model. And then you can just look over the PyTorch data loader, do your normal training steps. So this is very standard. And here I'm going to show a mini training example on a 4 years old single GPU computer, just to show that the training can be run. So if we scroll all the way to the bottom, you can see that it's reporting iterations, it's reporting losses. Yeah, the training is ongoing. So yeah, I'm going to interrupt this. And the user you can also look at the training results through the TensorBoard. Here I'm going to show an example TensorBoard for full training. So this is a cached results. So that you should be able to reproduce these results by following our training example. Okay. So these are all 3 demos that I want to show today. So to summarize, we have demonstrated that pre-processing Aria data with ATEK is as simple as just modifying the configuration file. And we also provide this ATEK data store where you can directly access pre-processed PyTorch-ready Aria datasets. And finally, we have shown how to do model inference training and evaluation using ATEK library. So yeah, hope you enjoyed the demo, and then I'm gonna hand back to you.
Thanks, Xiaqing. That was great. Thank you. All right. One more thing I wanted to talk about before I hand things off to Zhao here. We might take a moment for the HDMI to kick in. Okay, Project Aria is now on Hugging Face. For those of you that use Hugging Face, we've set up a project here, and we have a lot of models and data sets already on here. And you can keep an eye, follow this, and you'll see more and more up on Hugging Face soon. And then just to recap, if you want to use Aria Research Kit, you can apply on our website at projectaria.com/researchkit. And we look at applications all the time, and we're just looking for good, motivated researchers that are looking to do novel things in the egocentric research space. And we're seeing a really broad range of things that people want to do. It surprises us, things that go beyond even our core competencies. And we're just excited to see what the community can do. So please apply if you have interesting research ideas, and we'd be happy to talk to you. And then if you're not quite ready to apply for the kit, really go on and take a look at our data sets, and you can start working with egocentric data right away. So just have a look at our website. And we're really excited to have you join us on this egocentric journey. Okay, so next up, we're going to have a talk from Zhao, who's going to go through the digital twin catalog in more detail. We'll do that, and then we'll have a break around 3:30. 3:30. All right.
Hey, good afternoon, everyone. My name is Zhao Dong. I'm currently a research scientist manager at the Reality Lab research team. Today is my great honor to talk about the topic. I put a title called the Democratizing Digital Twins. We'd like to talk to you about the path we have been working on and seeking to frictionless 3D digital twin creation for everyone. Before I start the talk, I want to say this is actually an XFN collaboration work across various Meta-RR teams, actually, for the Digital Twin Catalog project. It's my great honor to be here, to be able to talk to you and show you some great progress. Okay, so let's first start to define this 3D digital twin. A definition for this should be a highly detailed virtual representation of the physical world object or environment. It should accurately capture the shape and appearance of the object or other property of the object. For example, this is, I think James already showed this in his slides, you will see this kind of side-by-side comparison between the real photo and the digital twins. They match very well. And also, because of that, it should allow the visualization, analysis, and interaction as if it were real. Based on all this capability, we should be able to enable various downstream applications like simulation, e-commerce, or design. We have been looking into the digital twin creation research for quite a while. Now, I want to show you a demo we made for Mark Zuckerberg in the 2022 for the Connect.
All right, so we're going to scan Teddy. Not just because he's super cute, but also because he's got the right dimensions and level of detail for what we're trying to replicate. So here's how it works. So we just scan him on the phone. And that's about it. Right now, this takes some processing time, so we got it ready beforehand so we could check it out. Oh, wow. The level of detail on this is impressive. You can kind of see all these fine elements of it, like each individual strand of its hair. And you can even see through the semi-transparent bow tie that he has on. It's pretty awesome.
Yeah, it's just a beautiful reproduction. The second technology captures geometry and appearance directly.
So here we used a different technique called inverse rendering to scan an object into its digital twin and then bring it into augmented and virtual reality. And it responds dynamically to the lighting in the VR environment. And when you throw it in the air against a wall or if you bounce it off the ground, it's going to respond the same way that the physical object would. So we use Spark to put the virtual object next to the physical one here. They're almost identical.
All right. This is actually a demo we did for Mark to showcase our digital twin creation technology like 2 years ago. We've been trying to enable people use a mobile phone to basically to capture a video of the object. Then we can create the photorealistic quality of the digital twin of your physical world object. After that, I even pushed a little bit further. I think I made the teddy bear to be, we made the teddy bear, we can change the appearance of the teddy bear. And also you can add some physical property. You can basically make the teddy bear jump like a rubber bear, actually in VR. All these things actually showing in the VR headset. It's just a recording here. All right. So as you can see, we talk about the 3D digital twin should have multiple properties, right? It should have like 3D shape and appearance of it. It should also have like a physical property, just like a rubber bear we just showed. But also, you want to interact with this kind of digital twin object in your virtual environment. If you are human or the object need to interact with in the real environment. In this case, you also want to know its functionality. So a qualified digital twin will have all these property. But again, nowadays, the digital twin research is still in a very early stage. And for today's talk, we want to focus on 3D shape and appearance. That's like a starting point. That's a foundation to build up all the following properties. All right. So nowadays, if you want to build 3D digital twin, it will be actually pretty difficult to do it manually by artists. It's very challenging to match exactly the appearance, for example. So an automatic way nowadays to do this is one way is to try to using the 3D professional scanner, like what we show in the video. You can just scan this object, get this kind of all this shape and appearance property. Another way is like how to say you can use a cell phone the camera, everybody has a camera in your pocket. You can use it to a kind of video capture by yourself, do a careful capture of that. Then you can do in the reconstruction algorithm, we can reconstruct it. That's what we did for Mark, essentially. However, if you think about all this technology nowadays, right? If you think about for the dedicated, expensive lab setup for that professional scanner, it's actually very high, extremely high workload. It's certainly not for most people, actually, right? For the high-end camera, yes, we have cell phone, but even when we have cell phone, you actually need to do a careful capture of this object that still needs certain effort. So still not very easy for ordinary people, like say for my mom. It's so difficult for her to do this kind of thing. So the question we really want to answer is like, how can we enable frictionless 3D digital impression for every person? I think we have been thinking this for quite a while. The first answer coming to us is egocentric based acquisition device. It's actually, I think James already did a great introduction about all this Aria glass. I think I don't need to repeat it. We think the easiest way when you're wearing the Aria glass, the easiest way for you to capture the object would be you just look at it, essentially, right? That's you do not need to hold anything in your hand. You just use your eye to look at something. Then you will be able to reconstruct it. That's egocentric, make total sense. But if we think about if we taking this kind of egocentric Aria glass as a capture device, so what kind of acquisition mode it looks like? The first mode, we are trying to mimic this kind of cell phone capture mode. We call it active observation mode. For example, this is a sequence captured by Aria glass using the active observation. You basically do a little bit zoom in observation distance, and you basically do an inward facing 360-degree capture. You're going to on purpose zoom in a little bit, look at the object. Yeah, that's still an active observation, trying to mimic the standard inward facing 360-degree mobile phone capture style. Another way, we think is even more casual and probably is much simpler for people. It's like you just need to walk to that object, look at the object, don't need to get in closer, look at the natural observation distance. And you can either do a half circle, look at the thing, or you do a full circle, just walk away, essentially. This is what we call the passive mode or casual mode. We think that's actually the mode which you do not want to spend much effort, just want to take a few look of the object. You can reconstruct it. All right. So after we know in this capture mode, let's take a little bit closer look at the device, right? The first step, if we want to do the reconstruction, you need to know two things. You need to have very good quality to sense the data, like your image, for example. Or the second thing, you want to have very good camera pose. That's usually the two fundamental things, the precondition for your high quality reconstruction. If we look at the Aria RGB camera sensing, you already see a bunch of this kind of Aria RGB data. So you will see it has a bunch of spatial property compared with this mobile phone camera. For example, you have wider field view. You see that kind of fisheye-like image, right? It also has motion blur because you're wearing a glass on your head. You can easily shaking it. It's not that stable, actually. Another thing is that it's a rolling shutter camera. It's not it's actually, this also will potentially introduce some kind of artifact at a certain case. And also it has its own sensor noise model, have all the standard vignetting effects. And you also need to do the white balance. Finally, you want to do a very good calibration. So all these are the property, if you really want to use like egocentric Aria glass to do the high quality reconstruction. After that, you also want to get a good camera pose, right? A good thing like James already introduced, Aria has both SLAM camera and RGB camera. In this way, you could use in the SLAM technology, basically Aria already provide very good, very accurate pose estimation technique through the API, essentially. You can use SLAM to estimate the pose. Additionally, Aria also provide other like motion perception signals like eye tracking or hand tracking. This could be later for even more natural interaction with the object's reconstruction. So since we don't have much time, we would like to focus on one of the important property which will impact your reconstruction result is the motion blur, essentially. That will basically decide your quality of your reconstruction. And also, since egocentric based 3D reconstruction is a pretty new topic, I don't think we did not see people actually do this before. People do not have high confidence about whether they can use this kind of device to get a very high quality reconstruction. So today we want to show you some of the research progress already made and share some experience we already had, actually. Let's look at the motion blur. As I said, when you're wearing your glass in your head, you have a significant head motion. Actually, we have this kind of Aria daily activity dataset, which is basically called the pilot dataset, which is basically record your daily activity when people wearing the Aria glass, trying to record all this kind of sensor information. Based on that, we actually noticed the blue line basically shows like basically the nozzle rotation velocity. You see the x-axis is the rotation velocity. You see actually the nozzle actually this kind of head motion happening in your daily activity. So due to that caused the issue, which is how to say, even with a very short exposure time of 5 milliseconds, you see the red dot here. You don't need to read the whole graph. The red dot I point out is like the 35% of the captured image. The only 35% does not have motion blur. So that's actually it's not a very good signal for you, right? So all this data internally, we have a team did a very comprehensive analysis. There will be an upcoming archive paper about it. Actually, we are going to release very soon. So what can we do? Motion blur basically ruins everything. We don't want the motion blur. Then what can you do? You can reduce the exposure time. But what's the consequence of the exposure time got reduced, even less than 5 milliseconds, which is noise. For example, if you look at this input video we captured using Aria glass, right? You see very noise input. Hopefully the projector shows that. It's actually quite noisy. Actually, you will see lots of this kind of image noise in the input video. This actually also causes our concern, right? Because the input noise will also impact your final results quality. But fortunately, based on a very famous work in the research domain, we call the noise to noise, essentially, because our sensor noise is actually quite uniform, actually, and distributed. So in that way, if you inject this kind of noise frame into your into doing this kind of high dynamic range Gaussian splatting reconstruction, you actually get a pretty reasonable result. If you look at the left, is the input noise is input. On the right side is the Gaussian splatting based dense view reconstruction. You will see the quality is actually pretty good. And that's a very interesting finding for us. So based on that, here you can see this is actually a Gaussian splatting-based dense view reconstruction of the radiance field of the two objects. From this quality, as you can see, this quality is basically match. So how to say, nowadays, if you're taking the professional camera or something to do this kind of reconstruction for that. All right, so seems like the indoor lighting, when the indoor lighting is dark, we need a very small exposure time. It's not blocking us doing high quality reconstruction. How about outdoor, right? That's another case we always see. Outdoor is very nice. Outdoor is very bright. So the exposure time can even less than 1 millisecond. We do not have a noise issue. That's awesome. But the following problem that if we do the outdoor, usually we want to look at the large scale scene reconstruction, which means that usually you need to handle 1,500 even to 2,000 photos to do the reconstruction. That actually poses a challenge for the traditional pose estimation technology like a cold map, for example. The cold map, we did the test for the same sequence. The cold map takes 4 days, almost 4 days, to running on a very powerful AWS GPU to give us this kind of pose, all the pose for the sequence. But for the Aria, we have this kind of machine perception service SLAM technology. Actually, we only take about 20 minutes. We already get all the camera has been very well calibrated. We get a very accurate pose. Here is another example. As you can see, the reconstruction quality is pretty good, actually. All right, I think James already showed this. I just want to remind you again. For the Aria, we have been consistently improving the quality of the calibration, essentially. Like this, we have a new feature for called online SLAM plus RGB online calibration. Compared with the factory calibration from the original glass, the online calibration can fine-tune the pose very accurately. Here, I think James already showed this video before, but I just want to repeat it. if you look at there will be a moment you are going to clearly see when you have the online calibration, you are going to see all the details of the reconstructed scene. By comparison, if you look at the text, you will see the clear and the blurry difference. Actually, all these things actually impact the final experience of your immersion, just like Jen mentioned. Actually, all right. So we have the first answer. We think it's good, right? How to get the frictionless reconstruction? We think the first thing we want to rely on the egocentric, this kind of capture device. We have the second thought. It's like, because what we see so far have been using all the image, so we call the dense view reconstruction. Do we really need all the dense view, all the image to do the reconstruction? Can we just use a sparse view or small number of views to doing that, essentially, right? If the user only needs a small number of views, that will make this problem even simpler, actually. Yes. Inspired by the last year's very recent work we call the large reconstruction model, or LRM, we actually developed an improved LRM-based sparse view reconstruction model. Here in the image we show, when the sequence, we take a randomly pick 8 view of this birdhouse, actually taken as input. We're doing both the nerve reconstruction, radiance field, and also the mesh extraction from the volume SDF. On the right side, in comparison, it's like the standard and state-of-the-art nerve technique, and also the neural SDF technology. As you can see, even with 8 view, a small number of view, actually, our reconstruction quality is significantly better and already reached the satisfactory status. So by comparison, the traditional technology cannot handle this. For this new reconstruction model, LRM-based spatial reconstruction, we actually support both all the nerve, a different representation like a nerve, volume SDF, and also Gaussian. We trained using object-verse dataset. It's generalizable to arbitrary 3D case. And we improved it by improved higher triplane resolution and also enable the progressive reconstruction update. I'm going to talk about all the details a little bit. And a good thing for this is it's a pre-trained model, but the good thing for the inference is less than 1 second, essentially, testing on A100 GPU, which means like you can instantly get your model, actually. So here's another example showing case the radiance field comparison. This is not just another model, actually. This is all taking 8 area captured image as input. We basically reconstruct the 3D model here. So here we did some, how to say, more widely spread data set. It's like from GSO and ABO data set. We also want to do a validation test to see whether besides Aria data set, whether other data set also works well. Actually, as you can see, this is a nerve and the volume SDF result we get, all using 4 to 8 image as input. As you can see, the quality is always pretty decent. For the Gaussian we actually we implement Gaussian as a representation. It achieves like faster rendering speed and also have a shorter rendering time, training time, sorry. It's actually pretty good for representing highly detailed geometry or texture. As you can see, all the scene geometry and also the text actually on the box on the right are all reconstructed very well. We did a kind of PSNR number comparison. Compared with volume SDF, the Gaussian can reach a slightly higher PSNR. But honestly, if you look at all the PSNR numbers, they're all above 30. If you are very experienced for the 3D reconstruction, you know, if you're doing a reconstruction, you get a PSNR above 30, that's actually pretty good. Very good quality already, even for the very dense view reconstruction. But keep in mind, this is only like a sparse, we only take 4 to 8 image. So the next interesting research we actually identified is interesting is that we basically want to enable the updated model for progressive reconstruction. What does it mean? If you look at this video, okay, on the left side is the first set of the input image. As you can see, the first 4 input image does not see the backside of the birdhouse, right? So the model need to hallucinate it, essentially. But LRM is not, compared with the diffusion model, our findings, LRM is not that great at hallucination. But also actually sometimes it's impossible to know what is happening in the backside. So based on that, we actually developed our model to push for 1 step further. We enabled kind of progress update function. We're basically going to reuse the previous token generated by the transformer underneath, add a new token, and enable the kind of the progressive update. As you can see, if I take the second set of the input image, I just reconstruct to a progress update of the reconstruction. Right now, I get the correct results, essentially. This is actually pretty, even though it looks like kind of expected, but it's actually an important function in practice. Because if you think about it, it's impossible for you to always take a few random view. You can see every side of the object, right? If you want to get the perfect reconstruction rate, you always want to make sure your model can support the progressive update. Because if you have an always on sensing glass in the future and you are at home, you always will have opportunity to see all the face of your model. That we will get a very good quality reconstruction. Lastly, here is the real data, right? The top row is actually the Aria captured image. The bottom row actually is the DSLR captured image. So I want to mention one thing is like our LLM-based reconstruction model not only work for the Aria-based egocentric, it also work for the standard, this kind of mobile phone, whatever, or DSLR captured image. As you can see, we trained the model, all generates very well, take this kind of input, essentially. That's actually very encouraging for us. All right. I talk about some research finding we did, right? That's actually we feel very excited. We showed you, hopefully I give you some confidence. If you're using this kind of egocentric device, there's a possible path there. We could get frictionless, very high quality 3D reconstruction for the physical world object. But we want to do more than that, essentially, because we know doing the research nowadays in the academia domain is very challenging if you do not have very good data set to pursue research, essentially. Therefore, just like James already announced, today we also released for the Aria Digital Twin Catalog dataset. This is actually the highest quality dataset for the object reconstruction research so far, actually. So I will dive a little bit in the details about how the dataset looks like. So the dataset composition will have like more than 2,400 individual scanned very high quality 3D object. Then we also have like 400 objects fully compatible with the previously released the DigiTwin dataset, which is modeled by professional artists. They're also very high quality. Also, in the same time, we have like Aria recording of 100 objects, which including both active and passive observation mode. Even further, we want to enable you to do the relightable reconstruction, and you want you to see what is the upper bound of your reconstruction algorithm. We did a DSLR capture, or build a custom rig to do the DSLR capture with 50 objects on the 2 different lightings. All this data were also included in the dataset for your research. Finally, we provide some tools for downloading and loading this data and do the visualization. Let's look at the step by step. The first thing is the scanned object, essentially. We call it very high quality because it actually has ultra precise geometry. We go to millimeter level geometry accuracy. And also we have a full set of photorealistic PPR materials, essentially. So this is actually very rare in nowadays public data set available. So to generate such a high quality model process, we actually produce our initial 3D model through scanning using the Covision 3D scanner. After that, we're going to go through our in-house shape and appearance refinement pipeline. We develop a pipeline for ourselves to do in this improvement. Finally, the model, we are going to ask our professional technical artists to validate the quality of the model to make sure it's reached the DigiTwin quality we really want. The video basically shows a mosaic view of this kind of 2,000 object. That's model, okay? Besides model, we also have like Aria recording of the 100 objects, both active and passive observation mode. Nowadays, you actually can just go to this kind of Aria Explorer link directly. You will see all the captured Aria sequences there. It's very easy for you to check it, essentially. Also, as I said, to produce the upper bound reconstruction quality and also enable the inverse rendering of the reconstructed relightable digital twin. Basically, we also provide the DSLR capture of the 50 objects on the 2 different lighting conditions. This actually, as you can see, the photo is a custom rig we built by ourselves. On the right side, you will see the standard image, which is a capture high dynamic range, low dynamic range image, and the camera and object pose, foreground object mask, and also the environment lighting as shown on the bottom right here. So this, if you are doing the reconstruction, this is actually very standard format. Actually, you'll be very familiar with this. So also, to validate our DSR capture, we also validated the data using the neural PBIR technology, which is our ECCV 2023 work. It actually still achieves the best relighting and the surface reconstruction quality right now on the Stanford ORB dataset benchmark. So it's actually pretty good technology for validation. We validated the dataset on this kind of technology already before we release. So that's what last thing I want to talk about for the dataset is really like the foreground object mask. Because we understand if we want to do the very high quality evaluation, you're basically the foreground mask will help you to improve that, right? Sorry, the pixel-wise accurate foreground mask will give you kind of possibility to do the high quality evaluation. For example, this is basically the mask we provide for you, essentially. As you can see, this is actually, if you look at, this is the Aria sequence, right? You will see all this kind of highlighted area. It's basically the mask area. As you can see, we get a really high quality, pixel-wise accurate mask for you. This will certainly improve your evaluation quality. People, you might heard about Meta recently released the SAM2, Segment Anything 2, right? That's actually also a technology, a machine learning model, large model to give you the mask. In the beginning, we also want to resort to that technology, but we noticed that it's not that easy. On this comparison here, on the bottom left is our own approach to generate the mask, which has the highest quality. On the bottom right, it's called a video SAM, or SAM. That's essentially SAM2 technology. If you see the mask actually quality when you rotate the model, you will see our technology has been very stable, consistent. But for all the other technology, besides SAM2, also have like a publicly available remove BG, all this kind of other technologies, they're all non-stable. So we want to provide you the highest quality possible mask for you to do your evaluation. Therefore, we developed our own technology using neural mesh, a kind of neural mesh reconstruction method. This is another example. It's a teapot. It's the same. As you can see, our mask has been very consistent and very stable, essentially. Okay, so just like James already mentioned, download the dataset. It's available for you to try it and available to improve your reconstruction research. We're happy to hear from you about how you feel about it. We want to improve that. We know nothing is perfect. We're looking forward to the feedback, and we want to see how can we further improve to work with you together to push the whole field forward. So we also have something more exciting to show besides whatever we released today. Is we also are going to be released in the end of this year. Yeah, first thing I want to show you an Aria simulation pipeline. What it is, essentially, if you use the Aria glass doing this kind of capture, you really want to how to say, get your image to have the minimal domain gap with your input, right? Essentially, you train a model, you get some, for example, you use the synthetic data train a model. You want the synthetic data to have the minimal domain gap with your Aria input. So motivated by that, we trying to simulate the RGB sensing capability and the pipeline of the Aria RGB sensor. As you can see here, this is basically a synthetic rendering starting from the normal synthetic rendering case. Finally, after all these kind of steps, to trying to produce you the final image, which mimic and match the Aria sensing, RGB sensing results. Interesting, like for example, we also did a specific design for the noise model for the RGB sensing. As you can see here for the clean image, and also when you increase the sensor gain value, you're going to get more kind of noise. This is actually trying to match the real sensor noise pattern. For this video, we want to show you on the right side is actually the real captured video sequence. On the left side is actually what we simulated. Just want to give you a sense. With all this kind of simulation pipeline, you're going to get a very closely matching Aria sensing results using simulation data. So with that, right, if you have simulation pipeline, you can use it for example, you can even not only use it for our released model, you can also use it for Objectverse. You can use any 3D model for you. You can use that to generate an endless number of the Aria-based training data set for you. That's actually something we want, so a powerful tool we would like to hand it to you in the end of this year. Yeah, this is just a video showcase like 2,000 objects. We did this kind of simulation, trying to show you the results. All right, before the simulation pipeline, I think we want to share our knowledge. So we want to work with you together to push the field forward by sharing the knowledge. For example, we would like to release the code for the Gaussian-based density reconstruction. You already see the result in the slides. We also want to release the code and the pre-trained model for the LLM-based sparsity reconstruction. We understand GPU is actually a very challenging resource. So we will also release the pre-trained model for you. So you can fine-tune it, right, in that case. And we also will release the code for the neural PPIR method. That's still the state of the art for the reliable 3D reconstruction technology. Yeah, that's all will come in the end of this year. All right, I talked quite a bit, but I want to use this slide to give a heartfelt thanks to our incredible R&D, TA, Ops, RPM, and engineering team to help to do outstanding contribution to make this happen, essentially. I'm extremely proud to be part of the Digital Twin catalog team. That's my last slide. The future of the Digital Twin creation is here. So we invite you to join us on this exciting journey. Go ahead, download the dataset. We're looking forward to hear from you. Thank you so much.
Thanks, Zhao. That was great. Okay, so just another overview really quickly of our agenda. Okay, so we've got a break here for about 30 minutes, and then we'll come back at 4 o'clock and we'll hear from surreal researchers on 3 different data sets. This is going to be Prithviraj, Julian, and Lingni, who are each talking about Hot 3D, Nymeria, and also our egocentric foundation models. So enjoy your break for 30 minutes. Come back and hear from more of our researchers.
So good afternoon, everyone. Good afternoon, everyone. I'm Prithviraj Banerjee from Meta Reality Labs, and today I want to talk about Hot 3D, new benchmark for hand and object tracking. And I gave a condensed version of this talk in the BOP workshop in the morning. So some of you who are coming from that workshop might find some of the slides, same. So I would like to start by motivating why we need yet another computer vision dataset. With the advent of large language models, it has made the development of personalized AI agents easier and more accessible. However, the current generation agents do not really have access to the physical context of the user, like what is the person doing in the real world. So one of our goals is to accelerate the research on egocentric vision applications, such as developing personalized AI agents based on data coming from smart glasses. And secondly, we are also interested in developing a dataset which allows researchers to make reasonable assumptions for practical end-user applications, such as availability of multiple views from calibrated cameras, or the availability of time-synchronized multi-frame data. And while it's exciting to see the large-scale video recordings that are being created using all the different wearable headsets, looking at the sheer diversity of objects in these recordings, we are faced with a scaling problem. How do we really go about detecting and parsing all the objects in these videos with an eventual goal to develop a personalized AI agent? One solution is to only focus on objects with which we interact with our hands. For example, if you're looking at a view of a cluttered desk, we really only care about the objects which our hands touch, such as the laptop or the mouse or the phone. If you're walking down a grocery aisle, we only care about the objects that we pick up with our hands, or put it in our cart, or put it back in the shelf. We really don't need to parse the rest of the objects in the scene. So the hands are like a spotlight on the objects we really care about. And from that perspective, we feel that development of an always-on personalized AI agent likely requires a robust understanding of hand-object interactions. Unfortunately, the majority of the existing datasets focus either on hands or on objects independently. We want to address this gap of datasets by providing annotations for 3D hand and object poses involving daily use items captured via multi-view egocentric cameras. We introduced the Hot3D dataset, which contains 1 million plus multi-view frames of highly accurate hand and object annotations. Recordings from the Aria device will contain a RGB and 2 monochrome egocentric views of the scene, which you have already heard about in this workshop. The MPS machine perception service pipeline also provides us with the slam trajectory of the headset, a semi-dense point cloud reconstruction of the scene, and also the eye gaze trajectory of the participant. To the best of our knowledge, this is the first time a dataset is bringing together hands, objects, and eye gaze together into a single consolidated dataset. So to give you an idea of the scale of the dataset, I already mentioned we are providing 1 million plus annotated multi-view frame sets. It contains 3.7 million recorded images across all the camera streams spanning 830 minutes. And the dataset contains 19 participants interacting with 33 daily use objects with a cumulative object trajectory exceeding 13 kilometers. So how did we go about collecting this dataset? We used a motion capture system called OptiTrack, where we place 3 millimeter IR markers on the back of our hands and also on the objects. We built a custom rig to mount OptiTrack IR cameras to track these markers within a spatial area of about 2.5 by 2.5 meters. And you can see an image of the rig on the left side. And within this rig, we recreated 3 scenes from daily living. For example, a kitchen scene with a kitchen island and shelf with produce items on it, a workroom scene with a computer table and chair, and also a whiteboard to write on, and a living room scene with a comfortable couch and a couple of coffee tables. And corresponding to these scenes, we curated a list of 33 daily use objects. For the kitchen, we have the bowl, the potato masher, and spatula. For the workroom, we have keyboard, mouse, phone, whiteboard markers. And for the living room, we have a coffee pot, flask, and dumbbell for light exercise. And for all these objects, we provide high-quality 3D mesh models with PBR materials, similar to the DTC dataset that you saw in the morning. And these CAD models will allow the end user to generate synthetic renderings for both training and inference. And this image is, by the way, a synthetically rendered scene. And it still surprises me by how photorealistic it is. The dataset itself is collected using 2 headsets, Quest 3 and Aria, roughly split half and half. And this will encourage the community to experiment with the domain adaptation problem, where algorithms trained on data from one headset needs to adapt to another headset with a different camera configuration, which is a critical gap in the egocentric vision community where models developed on one headset only work for that headset. So we also provide researchers with a set of resources to jumpstart their exploration with Hot3D. First, the images and 3D ground truth are easily viewable and available for download from the Dataset Explorer. We also provide a toolkit GitHub repository with data loading and visualization scripts along with the Jupyter notebooks. And we have a tech white paper and archive which describes the data collection and post-processing steps in detail. Getting started on any new dataset is hard. And to ease this process and to also enable apple-to-apple comparison for benchmarking, Hot3D adds a set of roughly 3,800 curated 5-second clips, with each clip containing around 150 frame sets. And the clips have gone through a human-in-the-loop QA process, ensuring high-quality ground truth annotations for all modeled objects in hand. Besides, the clips can be downloaded from Hugging Face and are served in an easy-to-use web dataset format that can be directly loaded through PyTorch APIs. So, next, I want to digress and highlight a very peculiar challenge we face with the Hot3D ground truth annotations. Object visibility estimates are critical for accurate measurement of benchmark performance, as you do not want to penalize a method for invisible or occluded objects. The standard method to compute hand object visibility relies on rasterization of model scene elements, like the image on the top, but fails to account for occlusions caused by unmodeled elements, example, arms or the furniture in the scene. This limitation is illustrated in the image on the right bottom, where the green segmentation masks demonstrate the challenge of accurately determining the visibility. The mouse and the cup are occluded by the arm, and the standard evaluation will unfairly penalize algorithms on such images. To address this gap, we developed a solution based on propagation of object mask using the SAM2 video algorithm, and results are shown on the right, where the phone at times gets completely occluded by the unmodeled arm on some of the frames, but we are able to correctly identify that as not visible to the camera and mark it as such. This work was done in collaboration with Tyop Lee from KAIST University, and you can check out more details regarding this critical post-processing step at the link below. The Hot 3D dataset is now part of the BOP challenge. If you attended it in the morning, you would know already about it. And this challenge has been, has been going on since 2017, together with partners from academia and industry. And the BOP challenge focuses on the task of detection and pose estimation of seen and unseen objects in both model-based and model-free variants starting this year. The challenge deadline has now been extended to November 29th, and that's just 2 weeks after the CVPR deadline this year. So please do check out the website for more details. Compared to academic datasets used in previous editions of the BOP challenge, Hot3D introduces new research problems. Most notably, Hot3D contains multi-view egocentric image streams showing dynamic scenes with hands manipulating objects. The previous BOP datasets, the classical datasets, contain images of static scenes without hands, typically captured from isolated viewpoints. Also, compared to the existing datasets, Hot3D provides ground truth poses that are of a noticeably higher quality. In addition to the traditional 6-DOF object pose estimation problem with known object models, we also want to support research on model-free 3D object tracking and on-the-fly 3D object reconstruction. This is a far more likely scenario in a practical application where CAD models of objects may not be readily available. Hot3D offers reference sequences which show all possible views at each object, which algorithms can use for onboarding new objects. Specifically, we provide sequences showing a static object on a desk where the object is standing upright or in another position, and also sequences showing an object being dynamically manipulated by the hand. Model-free 3D object tracking is also a new challenge track at BOP starting this year with its own dedicated leaderboard, so be sure to check it out. And Hot3D is on that, it is a part of that challenge. The BOP challenge leaderboard is currently active with submissions from a number of different teams across tasks. So definitely encourage you to check it out and check out the rankings on the Hot3D dataset. On the right, we are showing some sample results of the 2D detections from submissions from CNOS and 6D pose estimation results from GenFlow. If you see the qualitative result numbers over there, there's still a lot of scope for improvement, and we hope Hot3D provides that productive testbed for experimentation. Besides the BOP challenge, we are also organizing a new hand tracking challenge at the Hands workshop, which focuses on egocentric hand pose estimation and understanding hands in actions. The Hands workshop is being conducted on Monday, tomorrow, in the afternoon session. The challenge focuses on pose estimation with known shapes and hand shape estimation with the Mano models, very popular in the hand pose estimation community. And the Hot3D introduces several new features and challenges even in this field of hand tracking on XR headsets. First of all, having a multi-camera system means that you can use multi-view information to improve accuracy and also resolve the scale ambiguity. Our dataset also includes image captured from different headsets. I already mentioned that. So it encourages the participating methods to generalize to different camera configurations. And since the user doesn't change during a tracking session, we also found that using a pre-calibrated hand shape to perform personalized tracking simplifies the algorithmic pipeline. So we actually provide pre-calibrated hand shapes for all the 19 participants who were part of the dataset recordings. Now, the BOP challenge focuses only on objects, while the hands challenge focuses only on hands. And it can be argued that it is beneficial to track objects and hands jointly. Like, it's obvious that when a hand occludes the object, it should be easier to estimate the hand pose and vice versa. Hot3D enables evaluation of that joint tracking task because, first of all, it provides ground truth poses for both hands and objects. And that is a step towards connecting the BOP and hands communities, which has been historically very disconnected. And to facilitate this connection, we use the same test frames and clips from Hot3D in the BOP and hands challenges. So besides developing methods for joint hand and object tracking, this will enable any participant of the BOP challenge to condition their object trackers on hand predictions from the hands challenge and vice versa. And in the future, we hope to see more joint challenges for hands and objects. Now, at the beginning of this talk, I mentioned that always-on personalized contextual AI requires a robust hand-object interaction understanding. And one of our goals is to promote academic research on this topic. So in that spirit, I want to present some additional tasks which are not tied to an existing challenge, but are great avenues for future initiatives. Tasks such as detection and tracking of in-hand objects, that is, identify objects that are being manipulated or moved by the hands of the user. To enable evaluations on such tasks, we are augmenting the Hot3D annotations with ground truth segmentation masks of objects that are only manipulated by hands. And this will help address key gaps in the community, like providing a standardized dataset for evaluating in-hand object segmentation methods, and also evaluating the accuracy of persistent 3D tracking of in-hand objects. As an example, we show results from the EgoHorse paper, which provides an open source implementation of an in-hand object detector and segmentation algorithm. The image on the left shows examples of true positive results, and it's worth noting that the model was not trained on Hot3D and is completely agnostic of object category. The images on the right show some typical failure cases, and I hope this encourages research in this field, as we strongly believe that this is a critical component for a long-term vision of developing a contextual AI agent, which understands how a user interacts with the physical world. I invite you all to visit Hot3D website for more details and also to take a look at the corresponding challenge websites we are organizing. We'll also be there at the Meta booth during the main conference starting Tuesday. So we welcome you to stop by and we can talk more about this. Thank you. And next, I will pass it to Lingni Ma, who will present the Nymeria dataset.
Hi everyone, my name is Lingni. I'm a research scientist from the Zurich team. Today, I'd like to tell you about a project called Nymeria. So this is a big team effort in Mental Reality Labs in collaboration with NTU, Stanford, and University of Tübingen. So hopefully by now, we have convinced you that we have entered the era of contextualized computing for future AR, VR, and AI technology. Now, to enable this paradigm, an important cornerstone is to actually understand your own body motion from the egocentric wearable devices. And this work is a step towards building the future. I'd like to motivate the problem of understanding your own body motion with this video. So for now, I want you to focus first on the egocentric RGB video, which is captured by me wearing the Project Aria glass, walking around a building and interacting with the scene. As you will see, my own body appears very little in the view. However, as you watch the video, you probably can figure out what am I doing, and now the green avatar looks very reasonable to you. How can this happen? This is because there is a very strong correlation between your own body motion as well as the egocentric perception. So now, if your brain can figure this out, how about machine learning algorithms? How can we train a model to start to do the same? And when I say do the same, I don't mean just a single state of the body motion, but rather maybe a probabilistic inference of all the possible states, since there is ambiguity in your observation. And furthermore, can we take this one step further? So instead of predicting things in the parametric human states, which is more designed for the algorithms and computers to interact, can we predict and describe activities and actions in a natural language space so that humans can start to understand these inferences and large language models can have an interaction with the inference result? So when we start to look at this problem, we realize that the dataset is actually the biggest bottleneck. The state-of-the-art datasets are often provided in isolated motion. They are staged in the lab setup. They lack the scale and often limited diversity, and also they lack crucial annotations for researchers to study this problem. Arguably, in order to build such a dataset with all these desirable features, this is a very challenging task. This is because you need to do motion capture in the wild, you need to properly synchronize multiple devices. You also need to know a way to accurately process your data to deliver high-quality ground truth and rich annotations. And above all, you need to do all of this at a scale. Now, with this in mind, I'd like to present you the Nymeria dataset. This is a massive collection of human motion in the wild, captured diverse people engaged with diverse activities at diverse locations. We provide accurate body ground truth as well as raw sensor measurement and language descriptions. Now, to help you visualize the content and quality of the data, this video shows you 100 snippets of the random sampled sequences from the Nymeria dataset. So obviously, there's a lot that is going on. So let me help you to break down the techniques behind it. First of all, we use Project Aria to capture the multimodal egocentric data from your head. This includes videos, IMUs, audios, eye trackings, etc. We use the machine perception services provided by Project Nymeria to process the data so we can obtain the accurate six-off device tracking, the semi-dense point cloud, as well as compute the gaze with depth. Next, we modified the Project Aria into a wristband form factor so we can capture all these good stuff from your wrist perspective. Now, this is motivated by A, to resemble the future wearable devices, and B, to accurately capture your wrist motion so that algorithms can better constrain the body tracking. With respect to motion capture, we use the Axon's inertia-based motion capture suite, which gave us the full body kinematics in the wild at 240 Hz. Now, this kinematic state is carefully retargeted into a parametric linear blend skinning-based human model powered by open-sourced meta-momentum library. Now, of course, we'll also do optimization such that the global tracking of the bodysuit is properly aligned with the area world coordinates. Then we add an observer who wears the area to capture the entire scene and action from the third-person perspective. Now, let me stress that all the devices we used in data capture are properly synchronized and localized in one metric 3D world. Last but not least, human annotators view the data and add dense descriptions about the motion, in-context motion of the data in a hierarchical manner. Now we have a technical solution to these challenges. Let me tell you a little bit how we design the content of the dataset. First of all, we come up with 20 daily scenarios to capture the richness of everyday life. Each of our recordings is about 15 minutes long, where participants perform one of these scenarios. They are provided with only high-level descriptions of the actions. This leaves plenty of rooms to capture the natural and authentic motion and interactions. Showing you in this video is the same person engaging with 6 different scenarios. Next, we scale up along the participant axis. We recruit 264 different people to perform the same activities in a slightly different manner. And while we recruit different people, we paid attention to make sure there's a balanced demographics with respect to their ethnicity, gender, height, weight, as well as their age. Showing you here is 6 participants engaging in 3 sets of different activities. Now, with respect to locations, first, we rent 47 Airbnbs to record data of people's daily life. At each locations, we record about 4 to 15 hours of data. These houses are typical single-family homes. They contain multiple rooms, multiple levels, typically have a garden. And now, once we overlay all the trajectories we captured at each location, you start to see how dense the motion is. Interestingly, if we further zoom in these locations, you will start to see the spatial clusters of the trajectories naturally merges. These represent the spatial distribution of where humans' head and wrist are. We not only capture data at family homes, we also capture data at a large campus building, which includes a cafeteria with open patio, offices, multiple parking lots, and several biking and hiking trails. At this location, we captured 20 hours of human activities from 40 different participants. Now, as I play the video, you will be able to see that what kind of different activities people do and how wild, what we mean by capture motion in the wild. All right, that's actually not the end. Next, we actually add narrations into our data set, which is aimed to build the connection between human motion understanding as well as natural languages. In order to do this, we come up with a hierarchical annotation schema. So at the finest level, we have motion narration. For this task, annotators are focused on describing very detailed body postures, interactions with the scene, as well as where the participant is focusing on. Next, we simplified the previous task into what we call atomic action. In this task, annotators are encouraged to use simple words to describe the action and interaction. At our course level, we have activity summarization. Compared to the previous two tasks, which are focused on 5-second clips each annotation, for this one, we ask annotators to view longer clips, typically of 30 seconds, and write high-level descriptions of the activity. Now, altogether, our human annotators have write descriptions for over 230 hours of motion in over 300,000 sentences and 8.64 billion words. And this number is still growing. Now, this brings me to the conclusion of the dataset. As it stands today, Nymeria is the largest dataset in the world of human motion in the wild. It's first of its kind to capture multimodal egocentric devices, fully synchronized and localized in a single metric 3D world. It is also the largest dataset with in-context motion language narrations. And above all, the dataset is created with very rigorous privacy and ethics in mind. Now, with this quantity of data, we hope to empower research in egocentric human motion understanding. You can start to imagine the dataset being used to build algorithms for egocentric body tracking, motion generation, activity recognitions, and understanding. But we believe these are only scratch the surface of the full potential of the dataset. Now, to make the story a bit more convincing, I'm very excited to share you two very recent research projects uniquely enabled by the dataset. The first work is called HMD2. This is a work that is, at its core, is a diffusion-based model that synthesized full body motion from a single Aria input. That includes the images, the camera, the device trajectories, as well as the semi-dense point cloud. Now, as I play the video, I'd like to remind you how little information these images are actually captured and how accurate the body reconstruction is. Now, because this is a diffusion model, we can keep sampling the solution space, which will start to look like a probability distribution of all the plausible states of human motion. The second work I'd like to share is called EGLM. This is a multimodal language model built for egocentric motion understanding. With the quantity of Nymeria dataset, we can start to think of modeling human motion as a language. What this means is we can start to tokenize motion and build it together with a language model to learn this new motion. So we can fine-tune, for example, GPT-2 or the LaMar language models. And once this is done, we can start prompting the language models to make predictions about human motions as well as in the language space, driven by the raw sensor input, such as just the input of the trajectory of your head or the images captured by Aria device. Now, as I play the video, what you're seeing here is the input on the left. You see the input to our language model, which includes the images as well as the trajectories of the head and wrist. And on the left, what you see is the comparison of the ground truth motion and the output of our language model in terms of parametric human motion as well as language description. Now, I hope with these descriptions, you're excited to explore the Nymeria dataset. If so, I'm very happy to let you know we have open sourced the full dataset. You can read out our paper, download the data, explore our code base, and very nicely explore the data on our online web browser, where you will be able to look at and filter the data in terms of what kind of property they have, and directly download the sample data from there. I'm also very happy to tell you that we're keep developing the dataset. So very soon, there's going to be a lot more new features coming up. And in this video, what is being shown here is an annotation. Is an annotation of the 3D bounding boxes, very densely annotated for each of the Nymeria scene. So very soon, we're releasing all of these 3D bounding boxes to help you build algorithms of human understanding together with the semantic scene. With that, I'll conclude my talk, and I'd like to thank very much for the Surreal team and all the different people who helped build this amazing work. If you're interested, please come to our poster session too. And next, Julian will tell you a bit more about spatial AI.
Hello, everyone. Today I'm going to talk about EFM3D, which is a new benchmark for measuring progress towards 3D egocentric foundation models. This is in collaboration with a lot of people at Surreal and Meta Reality Labs, and the core group of people, Daniel DeTone, Tianwei Shen, Nan Yang, and Chris Sweeney, as well as Richard Newcombe. Let me start by showing you Orion. This is Meta's first augmented reality glasses, which Mark just revealed at Meta Connect. The advent of such wearable computers enables a new source of context for AI that is embedded in egocentric sensor data. This is the future of human-centric spatial AI. Egocentric data presents a new and important category of data that captures awareness live from the ego perspective. With Project Aria, we are already able to collect such data. This data comes with fine-grained 3D location information, including camera trajectory and semi-dense points, as we've heard about today. The key properties of egocentric data are: it's always on. We want day-long continuous data streams in indoor and outdoor environments, not just a few minutes. The sensors are head-worn, so we will see natural human motion and egocentric viewpoints, which results in sparse partial observations and not fully covered scanning motion. There's no dense depth due to power and thermal limitations. And it's inherently dynamic, as we just saw from Lingni's presentation. You will sometimes see the wearer's body or other body parts or hair in the camera. As such, this data source is different than the often studied data from autonomous cars and indoor RGBD cameras. Autonomous cars have to deal with partial observations and dynamic scenes, but they are not always on, and the motion is constrained to roads. RGBD datasets are typically recorded with scanning motion in controlled static scenes with the goal of getting complete observability, which is not a luxury we have on egocentric data. So in other words, egocentric spatial AI is like shrinking your favorite autonomous cars by a factor of 20 and then reducing their AI compute by 1,000 times, and flying them around all day long in 3D, everywhere humans go, indoors and out, not just on 2D roads. This new egocentric data source presents the opportunity for a novel class of foundation models that are rooted in 3D space via fine-grained spatial information. Well, there could be many tasks powered by 3D egocentric foundation models, including ego-human motion estimation, as Lingni just showed. We focus on two core 3D tasks of surface reconstruction and 3D object detection in this talk. To measure progress of the community on egocentric foundation models, we established EFM3D, which is a benchmark with two core 3D egocentric tasks. EFM3D is the first benchmark to do so for egocentric 3D reconstruction and 3D object detection. To enable the first wave of ML algorithms to be trained, we release a large and diverse simulated dataset for training and benchmarking. The Aria synthetic dataset contains 160 hours of simulated data across 10,000 scenes. There are 580,000 3D bounding boxes with a total of 29 classes. We released this dataset in collaboration with ATEK in a web dataset format that you can just download and start training on with the ATEK library. We additionally, to benchmark, released the Aria Everyday Objects dataset that consists of 25 scenes and a total of 45 minutes of real-world recording that is annotated with 1,000 high-quality 3D bounding boxes in 17 classes. You can see the geometric accuracy by comparing the 3D bounding boxes with the underlying point clouds in this video. And you can also see that 29 doesn't sound like a lot, but actually it should allow us to get relatively good signal already on the performance of these algorithms. And as Lingni just mentioned, we're also annotating all of Nymeria to give you access to more 3D bounding boxes, more boxes. We also released the ground truth mesh for Aria digital twin sequences in the surreal apartment to allow benchmarking surface estimation on real-world Project Aria data that is tightly aligned to a high-quality CAD model of the room, so we can get accurate signal on the geometric accuracy. Together with the EFM3D benchmark, we propose a baseline method that we call egocentric voxel lifting. EVL leverages all the available data streams from Aria and inherits foundational capabilities by using 2D foundation models, in this case Dino, as a first step. And then to enable 3D reasoning, we lift these 2D features into 3D by unprojecting and aggregating them on a feature grid in front of the last camera pose. We additionally discretize the semi-dense points information into a free space and occupied mask using the ray and point information. And we concatenate these two inputs into a 3D volume that we can process with the 3D UNet, and then finally extract the desired signals, in this case 3D bounding boxes and 3D occupancy. Here you can see the inputs, the multimodal inputs into EVL, the semi-dense points in white as they causally are inferred by the algorithm. This is what the model sees. We also have RGB stream and the pose of the camera as visualized by the green mannequin that's inferred by HMD2, which you just heard about. But that the mannequin is not part of the input. With these signals as inputs, EVL predicts both the 3D bounding boxes and surfaces, and we can fuse them via a straightforward 3D bounding box tracker and TSDF fusion, as you can see here. This leads to a persistent global representation of the scene that's inferred incrementally using this model. Now we can evaluate EVL on this new benchmark. When we do this and compare EVL to related 3D bounding box detection methods that use, for example, single frames like QBAR CNN, video snippets like InVoxelNet, and points like 3Deader, EVL performs best. Intuitively, this is because EVL can leverage both the precise but sparse points information and fuse it with the image information in the backbone. If you look at the performance on the real-world benchmark, these models all do not really perform well. And so there's lots of opportunity for improvement, and we invite the community to contribute to this. A similar pattern emerges for surface regression. Here we show the ground truth mesh on the left and the mesh fused from ground truth depth. You can see that the ground truth depth fused mesh is very accurate, but it has holes. It's incomplete due to the sparse nature of the egocentric trajectories. When we run EVL on the same sequence, we get slightly blobby but complete meshes from this fusion. So we can see that EVL has learned to some degree to complete unobserved surfaces, which is a desirable property for egocentric data. We can also compare it to neural recon, which is the most closely related method. Even if we train both of them on the same data set, you can see that by leveraging the sparse point clouds information, EVL performs much better on these egocentric reconstruction tasks. Now, let's address the elephant in the room. What about nerves or Gaussian splats? The problem with these methods is that because they're optimization-based, sparse partial views are challenging without the learned priors. And the dynamics in egocentric data leads to foggy artifacts because typically we make a static world assumption. You can check out our paper Ego Lifter, which we present on Tuesday in session 1, for how to deal with some of these artifacts and get crisp reconstructions. Probing EVL's sim to real performance in the next videos. So here we show EVL running on real sequences in the surreal apartment. And you can see that now that as we walk into this new room, it's able to refuse multi-room sequences without destructive interference, which is important for real-world applications. Here, EVL is running on an indoor sequence, where you can note, if you look at the grayscale camera images, that the hands of the user are actually in front of the cameras a lot of the time, and EVL is robust to these artifacts of egocentric data. And finally, EVL can run on outdoor sequences as well, even though it's only been trained on indoor simulated sequences and perform relatively well. The learned shape completion that I just talked about enables complete reconstruction from egocentric casual capture, as can be seen here. I basically just walked through this room kind of looking around. It took 20 seconds to collect the sequence, and we get a high-quality reconstruction. The quality of this reconstruction can approach a 30 times longer scanning capture with the original rig that we used to reconstruct Replica, which is one of the highest quality reconstruction data sets out there. So you can see how powerful learned priors can compensate for these sparse, these long sequences that you need if you really want to get complete reconstructions. The learned priors are also very robust. So here we reconstructed 1,000 sequences from Project Aria and found that the model performs well across all of these. When we combine the learned priors with incremental fusion systems, as we have done, we can reconstruct at any scale. So here, the only limitation is a memory, really, for the fusion system. And since we use a sparse voxel grid for fusion, it really can fit a lot of reconstruction. So this is a 16-minute sequence walking through a whole office building, and it all fit and reconstructed well. So in conclusion, egocentric data presents a novel challenge for 3D perception. These challenges include always-on sensor data, natural human motion, which leads to partial observations, and dynamics from the egocentric perspective. We think that 3D EFMs can address these challenges by learning strong priors that are anchored in 3D by a robust pose and semi-dense points information, and incremental operation with fusion into a persistent global state. To measure the progress we released the EFM 3D benchmark and also release our model so you can try it out. You can go there right now and download the model, and the data sets are also all public. So basically have fun.
Okay. Now we're going to move into a phase where we're going to start to have some presentations from external researchers, some of our partners. Let's see if this comes up. Yeah. So next up, we're going to have Antonino come up to talk a little bit about EGO-EXO40 from the EGO40 consortium. And then after that, Dima is going to come up from University of Bristol and talk about egocentric recording in the home. And we'll have Francesco from University of Catania talk about a procedural wearable assistant with Aria. And then lastly, we're going to have Paul-Edouard Sarlin from ETH Zurich talk about LaMar Aria. So I'll go ahead and hand things off here to Antonino. Another thing I want to mention is it seems like there's more sparsity in the front up here, and then there are people sitting down in the back. So if anybody wants to kind of come up and fill up the front rows, so we don't have to have people sitting on the floor, if they'd like to do that, that'd be great. Yeah, I think that's it. Antonino, come on.
Hello, my name is Antonino. So in this session, I'm going to give an overview on the EGO-EXO for the dataset, which is another resource that has been collected using Aria. More details on that in a moment, and that you can use in your research. So I'll start by drawing your attention on the fact that human skills are something very important for us. Human beings chase human skills. They try to learn new human skills. They are fascinated by skills of other people in different contexts, for instance, in sports or in daily lives, such as cooking or arts and any kind of activities which requires some kind of knowledge, for instance, I don't know, to repair a bike and following a set of steps. Okay, so since human skills are so important, one question is, what if AI could understand human skills? And a couple of applications already come to our mind if we think about it just for a couple of seconds. For instance, one notable application would be having AR or MR systems guiding us through our daily activities or alerting us if we're doing something wrong when we follow, for instance, a procedure. Or also think about robots who could learn from us, who could learn by watching us or by watching YouTube videos of people, for instance, cooking your favorite dish. Now, in order to try to bring this ability to AIs, we need to first understand how we learn new skills. And one answer is for sure exocentric observation. So this is something we are very familiar with. If we want to learn something new, we watch other people doing it, and other people will teach us by showing us what they do. So the first kind of observation, we obtain them by watching other people. But also research tells us that since we are very young, since we are children, we naturally develop the ability of do what is called perspective taking, which means while we watch other people doing other things, doing some activities, we also imagine what their visual stimuli will look like from our point of view. So in some sense, beyond the exocentric perspective, the egocentric perspective is something that that plays a role even when we watch others. And of course, since we learn by doing and by trying, our own egocentric stimuli and visual perspective is also very important. Also, how do we learn new skills today? It's very popular to watch a YouTube video. So for instance, let's say you want to learn how to cook eggs. You may watch something like this. Let's see if audio is working.
Yeah. Generate and touch on the heat, nice and gentle, and just gently shake that. And that helps that non-stick to work its magic. Now, look at it start to blister and bubble, the heat's getting in. We'll turn the heat back down now. Now, hear that noise?
Okay. So in a video like this, and this is some kind of video which has been created by humans for humans to learn how to do something. It's very common to see this synergy between these 2 points of view. An exocentric point of view, which captures the person with their body pose as they perform the actions, and an egocentric point of view, or an egocentric-like point of view, in which we see the details on the objects that are being manipulated. And so by merging these two views, we can both put the actions in their context and see the details. So we think that modeling egocentric and exocentric perspective is a promising direction for human skills understanding for AI. But so far, there are some datasets available which try to do this, so to put in perspective, to put together both egocentric and exocentric points of view, but they have some limitations. Notably, they are usually not very large scale. Most of them are set in lab collection settings. So for instance, with graduate students collecting activities and in laboratories rather than in native environments, in environments which are, natural for that kind of activity. And this is what motivated us to introduce the EgoExo for the dataset, which is posed as a foundational dataset and benchmark to support research on multimodal perception of skilled activity. The dataset contains, as the name may suggest, egocentric and exocentric points of view of synchronized views of people carrying out some kind of activity. In brief, but I'll give more details in the next slides, we have both egocentric and exocentric videos synchronized, about 700 participants with diverse expertise. The dataset is naturally multimodal. We have authentic environments. So as you can see, this is a real like bike repair shop. It's not like a lab. And we have about more than 1,000 hours of video. So domains and participants, we considered 6 different domains: cooking, music, repairs, health, sports, and dance. And within each of these domains, we have more than one different activities, different tasks. So for instance, we have more cooking, we have different cooking recipes, different musical instruments, different repairs, procedures, and so on. The consortium, the EgoExo4D consortium, is basically very overlapped with the original Ego4D consortium, is distributed in the world. So this gives us an interesting perspective on this kind of activities. And for instance, we can get a picture of how people cook eggs all over the world, which means different geographic variations, different use of tools, and also different cultural variations. We also engaged different participants with different ranges of expertise. So from novices to experts, we cover 123 environments, and ages, gender, and ethnicities varies to cover a diversity of participants. The dataset is multi-view and multimodal. We collected the dataset using Aria glasses. We have different synchronized views. So this is an example in which you see different exocentric views of the same activity going on at the same time. And by collecting through Aria glasses, we have a wide range of sensors. And so we have an egocentric view. We have 2 monocular left and right cameras, which are the ones used for SLAM, eye cameras, which are used to estimate gaze, and then a wide range of sensors. We have different microphones, accelerometer, gyroscope, and more. And this is all synchronized. Now, the way this has been collected is through a protocol which automatically synchronizes the egocentric point of view coming from Aria glasses with exocentric point of views coming from GoPros. So there is a procedure by which we show a QR code to the different cameras before collecting, so that then everything that we do can be synchronized afterwards. Okay, we have, beyond the videos themselves, we have video language data, which is some kind of supervision. It's a first level of supervision before getting to the labels, the actual labels. And in particular, we have 3 forms of time-stamped language provided with the video: expert commentary, atomic action descriptions, and narrate and act. And I'll give you some details on the 3 in the next slides. So expert commentary, here the idea is that after a person has collected the video, we want an external expert to watch the video and provide us a commentary on what has been done and if some parts of the execution are good, if some parts need improvement. We collected this kind of feedback, and it looks like this.
Great footwork. He's using the dribble to set up his footwork and his shot, stepping on that left foot, bringing the ball up, locking his eyes and head up. He's already known where he's going to go.
And the idea here is to collect the language from the experts so that we can learn, from the expert in their own particular language and way to, and technical terms and so on. Atomic actions, in this case, this is similar to what has been done in the past with Epic Kitchens or Ego4D. We asked annotators to watch the videos and stop the videos whenever they found something that was interesting to describe, and then put a description of the atomic actions going on. And these are time synchronized as well. So this is an example of the different atomic actions that have been annotated in an example video. And the third form of natural language supervision is the narrate and act. So here the idea is to capture the language from the participants, so from the person who's collecting the video, rather than from the experts, to gather knowledge about the way they call their tools and how they carry out their activity. And so as a separate set of videos, beyond those in which people just collect the video and do not naturally talk while they do it, we also ask them to do some form of, to shoot a specific video, special video, which is some form of tutorial in which they explain what they're doing while they're doing it. This is a separate set, so it can be treated in a special way, because we know that by doing this, we can introduce some bias, but again, the goal here is to capture their language, the language of the participants. This is an example. Okay. Now, beyond the natural language supervision, we also provide a set of labels which have been collected in different ways, and we formalize research challenges for first-person skill understanding. We have four benchmarks, which are key step recognition, proficiency estimation, ego-exo relation, and ego body pose. So for key step recognition, we come up with that for all different activities. We came up with taxonomies describing the different key steps, and we labeled the videos with the key steps. So every video is, for a subset of the dataset, is segmented in this way. And also, we also labeled task graphs, so graphs explaining the relationships between key steps. So for instance, what are the preconditions of a key step, or what are possible future key steps. And these labels are attached to each of the labeled key steps. So for each key step, you know what are the preconditions or what are possible future key steps, or if there is a procedural mistake at that specific time. We have 3 different tasks for this benchmark, which are fine-grained key step recognition. The goal here is to train using both egocentric and exocentric video to recognize key steps. And then at test time, we only want to recognize them from the egocentric video. So we want to learn something extra from the exocentric observations. In the second task, procedural understanding, we watch an egocentric video segment, and we have to predict a list of key steps that should have been performed before the current one, whether the current key step is an optional one, if it's a procedural mistake, what are possible next key steps, and if there are missing key steps. And in energy efficient multimodal recognition, the goal is still to recognize actions, but with an energy budget. So the idea is to design methods which can turn on and off some sensors in order to minimize the amount of energy which is spent while recognizing the actions. The second benchmark is proficiency estimation benchmark. Here, the idea is to watch a video and try to understand if the person performing the video is a novice or an expert, or even if some parts of the video are good executions or if they require improvement. So we have here 2 tasks, which are demonstrator proficiency estimation. This is a video classification task in which the model takes as input the video and has to classify it as either novice, early expert, intermediate expert, or late expert. And the second task is the demonstration proficiency. Here we take a video as input and we have to temporally segment it to highlight the parts of the video which are good executions and the parts of the videos which need improvement, so which are not good executions. The third benchmark is the ego-exo relation benchmark. Here the idea is to put in relationship objects appearing, so the same object appearing from the multiple views. So as you can see in this video, we labeled some objects, some specific objects in both views. So we have segmentation masks across synchronized views. And also in this case, we have more than one task. In particular, we have two: correspondence and translation. In both cases, the idea is to develop algorithms which can find relationship between the same object appearing in the two views. So in the correspondence task, we have the exocentric video with annotated segmentation mask, and we have to predict the segmentation mask in the synchronized egocentric frame. And in translation, we only have access to the exocentric video, and then we have access to the segmentation mask in the paired egocentric video, but not to the egocentric video, and we have to predict pixel values under the masks in the egocentric video. So we have to understand how the object changes appearance in the two different views. The fourth benchmark is ego body and hand pose benchmark. Here we have annotated 3D human pose across the, of course they are in the common 3D space that is shared by all the views. And we also have specific hand poses still in 3D. And we have two tasks, body pose and hand pose. In the two tasks, the goal is to, from the videos, either exocentric plus egocentric or only egocentric, to reconstruct the body pose and the hand pose in the two respective tasks in the 3D space, in the 3-coordinate space. Very briefly, before concluding, some information on how to access the dataset. The main entry points are the website and the documentation. In particular, in the documentation, you find all the information about how to get access to the data, how to download a subset of the data, and how to explore it. The first step is to sign a license, and please mind that it takes up to 48 hours for the for your signed license to be accepted, because there are some checks that we have to do. And when it's accepted, you will get some AWS credential, and you will be able to download either the full dataset or a subset of it. In particular, for the latter case, we also provide a visualizer. This was developed for Ego4D and then extended to EgoX4D, where you can browse the dataset according to scenario annotations. You can select a data subset, and you can download a JSON, which is going to list all the different videos that you are interested in. And then you can also visualize annotations on the videos so that you can see if you are interested in a specific video or subset of videos. And then you can use the EgoX4D downloader, which is a command line interface which allows you to download the dataset, either the full dataset or a specific subset, for instance, for a given challenge, or a customized subset that you may be selected using the visualizer. We also have a forum where we give announcement, but we also try to answer to your queries in case there are some issues with the data and with the resources that we're sharing. And to conclude, these are some stats about the dataset. EgoX4D covers 740 participants, 123 scenes, 13 cities, 689 actions, about 1,200 hours of video, 5,000 videos. The length of videos ranges from 1 minute to 42 minutes. We have multimodal videos, so we have 7 modalities, 40 million pose labels, 3 language assets, 4 benchmarks, and the dataset has been collected by a broad consortium of 15 partners, and these are all the universities which have been involved. So this is all thanks to the collective efforts. And that's it, and thank you for your attention.
Okay, I realized that we didn't do any Q&A for any of the talks. So we're going to do that now. We've got about 10 minutes until the next talk starts. So any questions related to any of the surreal research or Ego XO40, we've got these two microphones that are set up for us. These are going to work for us? Okay, so maybe I'll have Antonino come up and Julian. And are Lingni and Prithvi here? Yeah, great. Okay. And then we'll give it a moment. Maybe in the meantime, would you like to introduce yourself and ask your question?
Yes, my name is Ignas, and excellent talks. I had a question about the Orion glasses. It was mentioned it will be always on. I was wondering how do you manage the battery life, and will it be possible to use for prescription glass wearers?
I don't know that I can comment on the details of that. What I meant to say by always on is that we imagine that the most value will come out of AR glasses and similar if you can wear them always on. And so that's the goal forward.
Next question. And this could be for any of the surreal talks or Ego XO40 so far, or really anything that came up today, or any questions you have at all about Aria Research Kit, the Open Science Initiatives, the datasets. Surely there must be one more question. Go ahead.
Hi, I'm Sakib from Northern University. So nice talk, and I have a quick question for regarding Ego XO40. So I've been working with the dataset for a while, and I'm just curious that when I see the video annotation, there's some inconsistencies, like some missing annotations. Like for example, in some videos there were hand pose, in some other videos there's not. So and also like there's some human labels like proficiency score and other labels which are missing in some videos. So I understand that like for the human annotation, the reason behind missing could be it needed more human effort to like annotate all the videos. But for other annotations like hand pose or body pose, those are, I guess, automatically like annotated with some algorithm. So I'm just wondering like what could be the reason behind those missing annotations?
Okay. So first of all, the project is huge. I don't know all the details. I don't know if there is somebody in the room which have worked on body and pose. I've not been working on that. As a consortium, we're aware that there are some inconsistencies. There are something to be improved about the labels. Is something that we are discussing. I've been working more on the parts on procedure understanding. I know there are a couple of issues also there. My understanding is that since the project is huge and there are different things involved and lots of human efforts, as you were saying, there can be inconsistencies. But I would suggest, I don't know, Dima? Yeah.
Hand pose and body pose are minimal? Okay. Oh, okay. So there's my idea.
But one suggestion that I can give to anybody who's interested in, any like specific details, I think in the supplementary material of the paper, there is a part which is like the credit assignment, which explains who has been working on what. Mm-hmm. So maybe a good way to get that kind of answer is to try to email the specific person, or if you can catch them here somewhere at this conference, that'd be great. I will not be able to answer very specific on that part, and sorry about that.
Yeah, thank you so much.
Next question. I will let the awkward space linger. Yeah, maybe it's getting close to the end of the day, huh? Okay. All right. Well, thanks for coming up for questions. Appreciate it. Okay, we'll do the next presentation now. This is Dima from the University of Bristol.
Wow, it's a busy room. thanks to the Aria team for inviting us to tell you about some of the work we've been doing with the Aria glasses, and you've already heard about the Ego Exo 4D. So I wanted to talk about unscripted recordings. That's something I am personally very passionate about. And I know these terms now have been used in the wild and real data and all these things. And I wanted to present what I think is an unscripted recording and then how we're using Aria for that. And if that clashes with some of the previous talks, forgive me in advance. So what's the distinction between scripted and unscripted recordings? In my mind, there should be no overlap between researchers and participants to get what we call an unscripted recording. Furthermore, preferably the researcher should not even be there, but that can be negotiated. More, there should be no passing of tasks, objects, expectations from researcher to participant. The participant should be working in their own favorite environment, in their home, in their work, whatever they are, with their own tools, choosing whatever they do in their own activities, and making the choice of what they're willing to share. So as a result, that does mean the poor researcher has no clue what they will get back, which tends to be always an obstacle to collecting unscripted recordings. And often these recordings get thrown away because, like, that's not what I wanted. That is what the researcher would say. The problem with not collecting enough of this type of data is we don't know what to expect. And you've heard that these devices are coming. You know, all the claim that these devices are not yet there, that we computer vision researchers have said to date, this claim is going to go away. These devices are going to be there. Are we ready for them? And I think we are not. Let me show you a little bit of a difference. And again, forgive me, this is for the benefit of everyone. So Hot3D, great piece of work, we're using it. But this is not real data, right? That's not what the person can be doing. Let's take the corresponding collection of someone doing a very similar task, right? Some of you might say, okay, that's similar. I don't know. You might think it's similar. And a computer will be able to figure out when we go in the wild that this is per somebody steering, right? And again, this is a great piece of work and we are using it to understand hand-object interactions. But are we ready? If we solve this task, are we ready for this? Are we ready for people actually collecting the data in the wild, deciding that they want to add a sauce, and then, this is too much spice for me, but yeah, but then deciding to add a bit of spice to their pizza. Are we ready for these devices that we promise people to send to the wild? So we've been trying to see how that is happening through the partnership with the Project Aria. And we set up this nice backpack that we give it to the participants. We wish them luck. We send them home. And that backpack has effectively 4 Aria devices so that they can collect enough footage before trying to kind of download the data. So they take what we gave, we asked them to record for 3 days. We actually label their Aria devices, day 1, day 2, day 3. We give them an overflow in case they use a lot. We give them a power bank, so battery lives, and an already set mobile phone. So hopefully they can do all the syncing. If you've used Aria, that you know there is a great app. And we give them a set of instructions. And again, as I said, wish them luck. We also give them a scale, but I'm not going to talk about this now. You might want to wait for what that is for. But the good news is it works. These participants are coming back with great footage, having received our great backpack and sending it back. And they often comment on the fact that, yeah, maybe they were confused at the very beginning, but what we're getting back is really great footage from people's homes. Fantastic. We see stuff that, again, we haven't thought that we're going to see. So, this is some bit of preparing some pizza. Being in Italy, this is very timely. But yeah, I see some of this footage and I'm like, okay, are we ready for this footage? And unless we collect it, I don't think we can answer that task. But you're going to tell me, okay, there is a big gap between the data we can collect with annotations and this data we can collect in an unscripted manner in people's homes without telling them what to do. And over the past year, we've been trying to see if we can bridge that gap. Basically, can we use current technology to move this 2D footage in a manner that allow us to utilize the 3D knowledge that you've been seeing with hands and objects? We're not claiming this is a solved problem, but we did really great efforts to achieve that. You might have seen our prior work, it's called Out of Sight, Out of Mind, where we took epic kitchens, and then we kind of lifted objects to 3D and we moved them. So this, if you're interested in the background knowledge of how we use estimated depth, we lift estimated depth into real depth based on the 3D scene, and accordingly we can lift objects to 3D. But if you're interested in this back idea, then you can know how we're doing it. Let's focus on the scenes we have in Aria. So Aria, of course, gives us great 3D reconstruction of the scene. And again, remember, these people collected over 3 days. So this is a summation, and we're grateful to the Aria team. When we started uploading stuff, I think there was like a bit of panic. But luckily, we can reconstruct all these scenes now, and then we can take these scenes and manually do reconstructions. Again, these are people's homes. This is not a particular setup. So we are reconstructing the surfaces, we are reconstructing the objects. We're working with a great artist who's actually providing us info like where is the bin, what are the drawers, where is the fridge, etc. So we're building our own digital replica, but again, this is after the fact, right? So we didn't know what these kitchens look like in advance. Then we are here lifting gaze, so you can see, this is a bit slow, I don't know whether you can see it, yeah, but you can see us then knowing where the person is looking at in this 3D reconstructed setup through the projected gaze, right? So we can see the gaze direction, and we can really know what the person is interacting with. They're now looking at the fridge, they're now looking at the drawer. Again, this is a level of detail that we think is quite sufficient for lots of our actions. It might not be pixel perfect, but we know that something is taken from the fridge to the countertop, and the person is now working with the home. So we're lifting scenes, gaze, hands, and that's through some very good hand reconstructions. And the hardest bit we've been working on for a few months now is lifting objects. So what you can see now, there's a lot of manual annotations here of when objects move, but you will see is we know where all objects are. So this person took this object, and then now they have placed it in the microwave. There is a combination of automatic and manual annotations to provide a level of lifting in unscripted footage in people's homes. Again, this is like the person is drinking, so we're tracking every time something is being used all the way until it is being put down. The only thing saying is coming soon. I'm sorry this is not yet in your hands, but you heard it here first. We're claiming that this will be the most detailed annotations of an unscripted egocentric dataset. We hope to share it with the community soon. Before I conclude, if you're interested, I know there was a topic about hands and objects and only focusing on objects that are interacted with hand. Gabriele will be on Thursday presenting Amigo. Amigo is an effort to really talk about only the objects that are interacted with hands, and these are learned in an online manner, in a semantic free manner, so we don't give them any names, but we relate them to locations in 2D. This is a 2D stuff, purely 2D. But this is a memory representation of the scene in terms of what objects were moved from where to. And this is one way to start looking into long-term video recordings. And again, I always get the fun to come and present and show you what's coming, but there is a huge team working really, really a lot to deliver high-quality data sets, and I'm grateful for their efforts, and very grateful for the Aria team for supporting us since we started this project, with questions, concerns, panicky emails, that hopefully we'll be able to deliver something fun for the community. Thank you very much. You want questions?
Yeah, you can do like 5.
It's a bit of difficult. Like I told you about something that's not yet there, but if you have specific questions, I'm happy to answer. Yeah.
Thank you for the great teaser on what's coming, right? So
it is.
On the same note, right? Like I see lots of cool data sets, and being a roboticist, I can't help but think that when will Aria release a data set, let's say, that takes these egocentric things and, as you said, lift the objects into physically simulatable things in Xiaqing or something like that, because it makes sense, right? Like if you have a camera that goes around the room, getting a physically simulatable environment is difficult because you don't know how the objects are going to behave.
Yeah.
But if you have like 12 hours of a room, then I guess that's good enough data to have physically simulatable attributes of those objects. So I was just wondering if you had any plans.
Absolutely. I think these are great ideas. I'm sure we can lift some of the objects up, but not everything. Like I see some of the footage and I see people grating a bit of cheese and I'm like, there is no way we can estimate exactly this, right? There are things that are really hard, but there is stuff like actual like objects for which we can know what the model looks like, for which there is huge potential. You say, when are we providing to the robotics people? We always say, when will the robotics people create the simulator that we can train synthetic data with? So I think we should probably talk together because we might be waiting for one another, which is an infinite loop.
Sure, we can talk more later.
Thanks, Dima. I'm curious how you think about annotating the objects in the scene. Like, to what level do you want to push it? Do you want to have only the things I'm interacting with? And as you talked about the cheese example, so there's a scale thing. So I'm curious how you think about it.
Yeah, so I think we should only focus on the objects you're interacting with. But if we record long time, you should be interacting with almost all the objects in your kitchen, unless your kitchen is as busy as mine and most of the things need to be thrown away, which exists. But let's focus on the things you actually use. In this project, we played the trick of annotating object movements. So every time you lift an object, you have a manual annotation until you put it down. And it could be, you've used it, but you've put it down. And we were impressed how accurate these annotations from manual people were. Like, they're impressive. Like, it's very easy. Lift until put down. I think we can very easily reconstruct objects when they're put down, right? Now, how we can integrate that when they are in the hand perfectly in 3D, I don't yet see anything possible without the knowledge of the object yet. Of course, if you have CAD model, we can. But yeah, when it comes to the cheese, great, I have no idea. I think, I keep watching that video and I say, I don't think any dynamic object reconstruction will get anywhere close in the next, I don't want to make bets, but 5 years is a good bet. So if you're starting a PhD, the cheese is a good starting point.
The nightmare cheese.
Yeah, the nightmare cheese.
So you're saying basically annotating teleportation. So
yes.
Like it's here and then teleports over there and this time step.
Yes. Which really gives us a very good understanding of when objects are static and dynamic and accordingly, it's a really good labeling approach. We have never tried it before. So it's when we betted for it, it's a good bet.
Yeah. And so did you say that the objects themselves are annotated, like, will it have like an actual shape of a mug there? Or is it more just blobs that are, because I couldn't quite tell from.
Okay, when the object is static, we can nerf it.
Okay.
Because we get to see it from different views. Mm-hmm. But that really depends how many views you see it from, if that answers your question. But it's not bad.
Mm-hmm. Yeah, it's a sparse view kind of problem. Yeah.
It's not sparse. If you put something and you go around your kitchen, you really see lots of views to be surprised.
Right.
Yeah. I'll hopefully. Yeah, it's not a solved problem for sure.
Okay. Thank you.
You're welcome.
Hi. My question is about like reconstructing objects that hands are interacting with. So initially you showed the Hot3 dataset and then the, I think, Aria dataset. Now, Hot3D would provide a lot of clean annotations, whereas what we'll get from, let's say, Aria, and these are likely going to be noisier as compared to Hot3D. My understanding on this is we probably need both kinds of data. Now, my question is about what kind of scale do you think we need, as in, for Hot3D, we can only annotate so many objects, but for something like Aria, you can get a lot more variation in different objects. So do you have any thoughts on this?
The bit on the right you've seen is our new dataset, so that's not the Aria dataset, but it's an Aria recording. I think we can get really high level of quality now with some of the new foundation models and with what Aria offers in terms of 3D reconstruction of scenes, etc. We can really reconstruct a lot, right? Is this going to be pixel perfect? No. Do we need pixel perfect? I think no. But come the question. I think what we will be providing is a way to scale. But again, this is a research problem, which we're tackling, but we're looking forward to sharing more. And again, things like Hot 3D are essential for us to know the limits of what we can annotate. But my worry always is if that is what we're working on, are we ready for real humans? And they are amazingly agile.
Yeah, sounds good. Thank you.
Thank you very much.
All right, next up, we're going to have Francesco from University of Catania.
So hello everyone, I'm Francesco Ragusa from University of Catania, and today I'm going to present our ongoing work on how to build a procedural wearable assistant using Aria glasses. So multimodal large language models have recently become a popular research topic. So these models use a large language model as a brain to perform multimodal tasks. Every day, a new multimodal large language model is born, pushing the boundaries of what AI can achieve, exploiting multimodal signals like text, images, or audio to solve complex problems. So beyond visual question answering, able to provide proactive interaction and support, naturalistic conversation are missing in state-of-the-art datasets. So actually, in our dataset, we have synthetic generated conversation using natural language understanding pipelines or exploiting large language models. Or moreover, this dataset comprises post-acquisition narrations. So current benchmark on egocentric vision, lack of a principal benchmark composed of a dual agent real conversation. So a personal assistant should be able to see what the user is doing and relate language and vision to contextualize questions such as what is this or what should I do now? Also, this assistant should be able to notify the user if he's doing something wrong or give a suggestion how to improve a step or a procedure. So for this reason, we are starting to study how to build a procedural wearable assistant. And for this reason, we are using the Aria glasses. So our aim is to acquire a new dataset composed of egocentric videos of trainees engaging in different procedural activities in which they are not expert or very expert, and differently from current dataset, which are narrated after the acquisition, conversation between trainees and expert happens naturally. So our dataset will be multimodal because we are capturing everything that Aria glasses is able to acquire, such as RGB, gates, hands, and also we are acquiring the gates of the expert through a Toby bar. Also, we are acquiring the conversation between trainees and experts. So we are acquiring the audio conversation, then we have a transcription to obtain the text. For the acquisition, we designed two protocols, proactive protocols and non-proactive protocols. The first one, so the first acquisition, the trainee does not have the knowledge of the environment, of the object, or of the procedures that he needs to perform. And the expert speaks freely with the trainees, suggesting next steps, instruction, where are the tools in the environment, and so on. And this step is necessary to give a context to the trainees. So in the second acquisition protocols, which is the non-proactive protocols, the trainee now knows the environment, the object, the critical step of our procedures. And this is the realistic settings that we wanted to acquire. So we are using different devices for the acquisition. So the trainees wear Aria glasses and perform the activities. And so using a smartphone, we are able to stream the RGB video to a laptop where there is the expert that observes the environment from the point of view of the trainees and is able to interact with the trainees. And also in this laptop, there is connected a Toby bar to acquire the gaze of the expert. So why are we using a smartphone together with the Aria glasses? Unfortunately, Aria glasses is not able to perform acquisition and streaming simultaneously. So we need another device to stream the point of view of the user. But the RGB video is captured only with Aria glasses. So for the acquisition, we set a custom profile in the mobile app of the Aria SDK. And in particular, we set a custom profile in which we are acquiring the RGB videos at 15 FPS, and also we are acquiring the gates and the SLAM at 30 FPS, and also we are acquiring the Wi-Fi, barometer, and so on. The only signal that we are not acquiring with Aria glasses is the microphone, due to the GDPR rules that we have in Europe. So after the acquisition, we obtain the VRS file that is sent to the machine perception services of Meta to obtain the SLAM or the gates. For example, here there is an example in Aria Studio, in which you can observe the SLAM obtained from the VRS file, and also the gates reprojected in the frame of the trainees. So since we are able to acquire the gates of both trainees and experts, so we align these signals in a way that we reprojected the eye gaze of the expert in the frame of the trainees. And this is very useful because we can understand where the expert focuses his attention while he's answering the trainee's question. So here, there is an example of acquisition done in a bakery where the trainee is asking some questions and the expert answers this question, changing the behavior of the trainee. So our goal is to acquire 100 hours of egocentric videos, considering 5 scenarios, and we engaged 2 experts for each scenario, and also from 10 to 12 real trainees for each scenario. So we choose scenarios where it's possible to perform procedural activities, and also scenarios in which we think that a procedural assistant could be very useful. The first scenario is a bike workshop. We found 2 procedures to acquire, which are replace wheel, lubrication brakes, and also replace chain. The second scenario is bakery, which the procedures are make tart and make biscuits. And as you can see, so there are in this scenario very specific objects related to that scenario, for example, the industrial oven or in very specific tools. The third scenario is assembly, in which we have the procedure assembly a chair and assembly a chest of drawers. And then we are going to acquire also the carpenter scenario, which we aim to acquire industrial procedures with machine, and acquisition starts very soon, and also kitchens, which we found procedures like make lasagna or make arancino, which are very Italian-specific procedures. So following the mainstream multimodal large language model benchmarks, we are going to evaluate human-level assistant with multiple choice questions, which facilitate the computation of objective metrics such as the accuracy. So from the audio, we obtain the transcription, the text, then we select the positive answer of the expert, and then we generate 3 negative answers. So the aim is that given an input, the video clip and the trainee's question, we want that a multimodal large language model is able to classify the correct answer. Also, we create a form which comprises this multiple choice question to submit to the expert, because we wanted to measure the expert performance to answer these questions. And in the first case, we submitted only the text. So the expert observed only the question and the possible answers. Then the expert can see also the video clip to contextualize the questions. In this way, we have a baseline to understand where is the human performance for this task. So that's all. Probably in a few months, we will have more work to show with you, more details about this dataset. If you have questions, I'm here. Also, during the week, I'm in this conference. Thank you. Okay. Are there questions?
Yeah, I noticed some blinking in your videos, and I was figuring out maybe it's due to the light frequency and the frequency.
No, it's only the resolution of the GIFs for this presentation, but the videos are quite high quality. There is not this flickering or this flashing. Yeah. Other questions? Okay. Thank you.
Oh,
sorry.
One question.
Yeah.
You mentioned 5 scenarios, I think. How do you think about making this more general? Because you started out with language models, multimodal language models. Like how will it generalize to other tasks that are not on your list?
So we don't want to generalize to all the scenarios. So we choose these scenarios. Consider that in these scenarios we can observe procedural activities, and so the aim is, I think, that we can an assistant specific for each scenarios.
Yeah, thanks.
You're welcome.
Okay, thank you. We have one more presentation from Paul-Edouard. And he's going to talk about LaMar Aria.
Hello, everyone. Can you hear me? Yeah, all good. So hi, I'm Paul. Thanks for making it to the final talk of the session. I'm from ETH Zurich, and I'm gonna talk about benchmarking, localization, and mapping. So we're interested in the task of visual localization. So essentially finding out where we are, where a picture is taken. So this kind of generic task where that might be faced by humans trying to find out, where they are in the city to be, for example, be able to navigate, but also by mobile devices like phones or AR glasses. And so typically by positioning or visual localization, we mean finding out essentially the location expressed with respect to a given coordinates frame, and represented usually as a 6-dimensional pose that includes a 3D position and a 3D orientation. And this is particularly important for AR, where we want to make virtual objects stick to the real world. So essentially, first for collaborative applications where we want to share content between users, but also, of course, if we want content to persist over time. So there, local SLAM, local tracking is not enough. We need a global reference frame common to all devices over time. And so, of course, visual localization is related to visual mapping. So the process of estimating a map, a representation of the environment, and usually to estimate a map, we actually need to know where the sensor was at a given point in time. So essentially, mapping and localization are highly interdependent. And there's a bunch of different algorithms for that. Structure for motion, SLAM, kind of 2 flavors of the same problem. One works with unordered images, another one works with sequences. SFM is usually more of an offline process. SLAM is more for usually a real-time use case on device with minimum latency, but essentially turning multiple images into camera poses and a 3D model of the environment. And so in nominal cases, I would say visual localization and mapping is pretty much solved, but and it's solved usually with high accuracy and robustness. But there's many scenarios that remain challenging, and these include, for example, appearance changes, structural changes. So you can see here, for example, furniture moving or a building being built where you have a construction site and objects that move around. We might also have viewpoint changes. So essentially many different kind of changes between the time where the query is taken, the query image is taken that we want to localize, and the mapping images that are used to build our map. Of course, there's also motion blur, occlusion, and so on. As it's been, I'm sure, mentioned in the previous talks, egocentric data comes with additional challenges. We need to localize regardless of a user action, and the user might, move very fast, have very fast motion, go into scenes that are completely textureless. Essentially, we don't have control over this. We need to localize any data, and might also come from very unconstrained views. Of course, if we have multiple different devices that we want to align together, we also need to deal with the fact that we have different cameras with different imaging properties, different sensors, so we need to be robust to these kind of changes. And AR usually has high accuracy requirements. We want really pixel-aligned localization such that it doesn't, any misalignment is not visible to the user. So perfect alignment between the real and virtual content. Of course, egocentric data comes with opportunities. We have temporal sensor streams, so sensors that capture data through time, and we also have multiple sensors, not just a single camera, but we might have GPS, inertial data, Bluetooth, Wi-Fi, sometimes even depth cameras. So many different modalities that we can fuse together and that are available not just at a single point in time, but continuously over time. There's another class of opportunity is that because AR devices or let's say devices that capture egocentric data are so easy for the users to wear, we can suddenly have a lot more data. We don't need expert users that are trained specifically to take images. We can just give them Aria glasses, for example, and they can just go around and record data, and then it's our task to have algorithms that are robust and that can handle any data that users capture. So we might have a lot of data, especially if we have a large user base. It's virtually unlimited, and data might be redundant. We might have users that come multiple times in the same space, so brings additional challenges also of selecting the best data for mapping. So it turns out that for benchmarking localization and mapping in the context of egocentric data, some time ago, when we looked at this, there were not so many datasets. Most datasets that are used in the field focus either on driving scenarios where you have very different motion patterns and sensors than in AR, or datasets come from crowdsourced there are crowdsourced essentially from different users that capture with different devices than what we have with egocentric data. So typically single isolated images or very small spaces like single rooms. So not really exactly what we're looking for. And also these datasets, they often don't have sufficiently accurate ground truth. So for in our case, we talk about ground truth poses and the ground truth 3D structure of the environment. Usually in these existing datasets, they were computed using structure for motion, SLAM. This is more of kind of pseudo ground truth. And the few datasets that have very accurate ground truth, of course, they're captured at a single point in time. They don't really have any long-term temporal changes. So when we looked into this, essentially, we came up with a new datasets that was released at ECCV 2 years ago. We called it LaMar, Localization and Mapping for AR. And in that dataset, essentially, we considered 3 large scenes that included small and indoor, outdoor spaces, an office building, a university building, a whole city center of Zurich. And so we gathered essentially a lot of data. And back then, we didn't really have Aria devices. That was essentially, we started this 3-4 years ago. So all we had were HoloLens devices and phones, regular consumer phones. So we gathered hours of data over more than 1 year from users that were navigating these spaces. And then, of course, all these devices, they were equipped with different sensors, multi-camera rigs, depth cameras, initial measurement units, radio receivers like Bluetooth and Wi-Fi. And each device would continuously record this rich sensor stream over time, but also local odometry that runs on device in very unconstrained trajectories. No really guidelines given to the users. They can just do whatever they want. They can run, they can walk, and these are very different users. So we would have essentially long trajectories spanning hundreds of meters, both indoor and outdoor, that were all accurately registered in a common reference frame with high accuracy using detailed 3D models that we acquired using laser scanners. So all of these would be piped essentially into some kind of pipeline we designed that would globally register all these trajectories with centimeter accuracy, fusing essentially these sensor streams with the laser scans. And essentially, despite very challenging viewing conditions, the process was entirely automated. We would have no annotation, no manual annotation of any sort. It would just take the sensor data and then compute ground truth poses and 3D structure. And of course, we would know then the pose of each sensor over time and the 3D geometry of the scene. So we could, for example, verify the accuracy by doing renderings from the sensor poses and comparing them to the captured images, both in terms of color, depth, kind of checking that everything is well aligned. So this was quite some time ago, and so essentially, if we look at the process that went into building this data set, first we thought, oh, let's create a data set. That's easy, right? We just need to go out and capture some data, right? Actually, we all know, I guess, here how painful building a data set can be. So first we get devices, but of course these devices, HoloLens, phones, they are not really meant to be used for researchers to capture data. So we actually had to write our own tools to get the sensor data and do so in some kind of efficient way, such that we could capture a lot of data over time. Then we would actually go out and capture the data. Then we would need, of course, to anonymize the data because a lot of this data is captured in public spaces. And then we would actually develop the algorithms and run the algorithms to compute ground truth poses and 3D structure, such that then the data set was ready to use. Turns out that actually nowadays Project Aria makes this a lot simpler. So I'm going to go through each of these different points and kind of cover how basically if we were making this data set now, how much easier that would be actually compared to some time ago. So back then, essentially, we had no really nice tools or apps to capture data from, for example, Apple devices and get all the sensor data from ARKit and so on. So, of course, we wrote our own app. But then we have a burden of maintenance. We have additional efforts that are required if we want to cover new devices, add new sensors. It doesn't necessarily scale very well to hour-long sequences. So you always need more engineering efforts for this. Nowadays, I guess Aria makes all of this super simple because the stack actually comes ready for researchers. And that's something that we really realize now because we went through the pain of actually maintaining and creating our own stack to record data from consumer devices, which was very painful. Next comes the data anonymization. So if you want to release data, you probably need to blur faces and license plates. And it turns out that when we looked into this, essentially open source options were not really so accurate. They would miss too many faces, or they would blur the entire image such that it would be completely useless for downstream evaluations. They would not handle things like motion blur and large diversity of imagery, high resolution, low resolution, grayscale, and so on. And commercial options were first not that more accurate and actually quite expensive at scale. And then essentially Meta released Ego Blur, so this kind of open source models that make it possible to blur faces and license plates yourself. Of course, open source with a permissive license and actually fairly accurate, more accurate than a lot of the options that we had tried at the time. So this made things, this would make things nowadays a lot simpler. Then there's a problem of the sensor APIs. So essentially, even though a lot of these consumer devices, they have all these sensors, they don't necessarily expose these sensors, or they don't expose them in the way you need them. You might not have access to the raw sensor data. So typically with Apple devices, we don't really have access to nice IMU calibration parameters. We don't have access actually to raw Bluetooth or Wi-Fi signals. We can't do really too much with that. And same goes for HoloLens. Of course, also these devices, they have SLAM systems that are optimized for on-device use, so fairly unreliable and fragile when you actually consider very, very wild motions. And of course, Aria makes all of this a lot simpler, we realized, because first, Aria exposes all of our raw sensor data. It really hides nothing behind some obscure API. And through the machine perception services, it offers very strong offline SLAM system, much stronger than what we would get on actual consumer devices. So, of course, because we didn't really have access to overall sensor data, the calibration, and because these on-device LAMP systems were not so accurate, to actually build ground truth and register all these sensor data into a common reference frame, we had to rely on laser scans. So essentially, we got our hands on some mapping platforms from Navis, essentially a trolley or a backpack, and then essentially we would need to go around for an hour or two, scanning the entire space quite precisely, just to have ground truth 3D structure that we could use to align our sequences. And of course, these are proprietary systems. They don't expose any notion of uncertainty, makes it impossible to actually tweak and customize the optimization. It's kind of a pain, and it's also very tedious actually to scan these spaces. You need a lot of training, and it's not really. It means that we actually cannot just give these devices to people and pay them easily. We need mostly to do it ourselves. So it turns out that Aria actually makes all of this simpler nowadays because it has this MPS multi-SLAM system, right? So essentially you can directly upload multiple sequences and they will already be registered in the same reference frame, which is essentially what we spent so much time developing back then for our different sensor data. But even better, actually, since the full sensor data is available, we can write custom optimizations if we think that we can do a better job than the MPS multi-SLAM service, which still provides a pretty good initialization. So with all this in mind, essentially in 2024, we've decided to essentially create a second iteration of a dataset, building on top of Aria and the lessons we had learned with LaMar. And the idea is that since Aria makes it so simple to do all the steps we considered, we can go a lot further suddenly, and we can actually tackle more interesting problems. So this time we're focusing on mapping instead of localization. How do you go from raw sensor data to camera poses? So this is a little bit closer to SLAM, which works on sensor streams and sequences, than to structure for motion, which would work with unordered images. And here we really have much higher quality of data compared to version 1 that we had with LaMar. Essentially, we want to tackle larger spaces. That's where current SLAM systems are breaking. We want data that really pushes the limits of what current open source systems can do, such that we push the research community to build SLAM systems that can really scale. We want to have extreme motion patterns that really are not found in current datasets, but that are so important for egocentric data. And of course, we want even more accurate ground truth. We want to go down to the centimeter level instead of decimeter that we had with LaMar. So here, I'm showing a couple of sequences that we've recorded already. This is an aerial view of the city of Zurich, and we're basically considering sequences that are something like 2 kilometers long, maybe an hour, maybe half an hour, walking through the city in one go using Aria glasses, and then that are essentially all registered in the same space with centimeter accuracy. If you compare that to what we had with LaMar, these red areas were basically the scenes that we had with LaMar. So this is almost an order of magnitude larger. So we're really looking at scenes that are much larger. And of course, since now we have Aria, it's much easier to just give devices to for example, students at university and let them walk in the city for an hour and just record any data in the city. And then, of course, we can piece that together. So one thing that is so important to have such high accuracy is to actually go look at what people in surveying do. So essentially, the key ingredient in this is to use control points that are distributed throughout the city. We measured over 300 control points throughout Zurich, each with 1 or 2 centimeters of accuracy, using GNSS RTK sticks. And then we can essentially use these control points to anchor the sequences. So we're still capturing more data. Expect something to come out at some point, a new data set to benchmark visual inertial optimization and SLAM at scale. That's it. So LaMar was a collaboration between ETH and Microsoft, and now, of course, LaMar Aria is with Meta. Thank you so much. Yeah.
Take a couple questions.
Excellent work. A sort of amazing data set. I was wondering, did you do any comparisons of the sort of accuracy of the camera localization you can get from Street View data before you go out and collect your sort of high quality data? Or was there any reason why you didn't, let's say, map the video streams to Street View data to obtain your camera?
What do you mean exactly by Street View data?
So in a Street View, you can use Google Street View to actually sort of do structure for motion at any scale. And I'm wondering why do you chose to collect data from sort of scratch and invest so much time in making it very accurate? And so if data was fine, maybe you measured how accurate or inaccurate Street View.
Of course. So generally Street View data is captured by cars, right? If you're talking about Google Street View, for example, but same applies to Mapillary. So that doesn't really necessarily reflect the kind of data that we have as captured by egocentric data devices like Aria or AR glasses in general. Second, a lot of this data is actually not really usable in the sense that, for example, Google Street View data, you're not really supposed to use it for research unless you get special approval. This is not really, you cannot use it necessarily for commercial use, commercial applications. So we're more interested in getting data that actually the whole industry can use to evaluate their own systems if they want. So it's quite important to have data that has really the most permissive license possible. And of course, Street View data, if you were talking about using the poses that platforms like Mapillary or Street View expose, we have no guarantee on how accurate these poses are. And my personal experience with, for example, Mapillary is that a lot of this data is actually not that accurate. We're talking about maybe a meter accuracy, which is far insufficient to actually benchmark algorithms like SLAM nowadays. Yeah, but yeah, great point. Thanks.
Yeah, thanks for the cool talk. I'm curious, I've never thought about calibrating against these control points. Can you talk a little bit more about, because you can measure their location, but how does Aria know about that location?
So essentially you need to be able to detect these control points in Aria imagery, right? So that you can constrain the pose of a device. What we do is that we can either label the control points manually in a few images, but what is more interesting is to use things like April tags or like fiducial markers that we can place for a very short amount of time on the control point, such that then it can be actually automatically detected on any Aria imagery that is in the vicinity, and then we can essentially automatically link the control point to the device pose.
Oh, okay, so you measured out some kind of fiducials kind of before the recording, essentially, right?
Yeah, we can just place them right before the recording.
Yeah.
Or maybe we'll have two people, one working with the device and one working ahead and placing the fiducial, a few minutes before. It's a little bit of logistics, but in the end that works very well, even for very long sequences.
Cool, yeah, thanks. And so you mentioned it gets down to centimeter precision. So I'm curious, what's the limitation there, and have you thought about pushing further?
One of the limitations is that you actually need to go and measure the control points. So here we're quite lucky because in Switzerland there's a public registry of control points throughout the country. So essentially in Zurich we have 10,000 control points that are publicly available, all within a few centimeters of accuracy. So we still went and we actually re-recorded plenty of them. That's the 300 points I showed to just be sure that actually these are reliable. And it turns out that yes. So we can actually scale to a much larger area using public control points. We still need to go with the fiducial markers, of course. So this is not really fully unconstrained trajectories in the sense that you still need to go through control points, and so that adds some peculiarity to the data. But I think that's the price to pay to have such accurate ground truth at this scale, of course.
I mean, how are the public ones marked?
There's different types. You can have, for example, kind of steel bolts that are in the asphalt, or you can have like pieces of stone, basically stone with a hole in the middle. There's different types of them, but it's all nicely documented. And I think this kind of thing is available in many other countries, of course.
And getting back to the second question of how do you go beyond centimeter resolution? Do you have any thoughts on that?
Higher, like even more accurate than 1
millimeter. Yeah.
This I don't know. We don't have. Well, it depends. Of course, if you're talking about small interspaces, you could have a Viking system, and I think with the new systems, very small scale, you can probably get down to 1 millimeter. Or if we're talking about 1 millimeter at the scale of a city, that's going to be complicated.
So GPS is kind of the limitation.
Well, actually, we don't use any GPS in the sense that the control points tell you where you are exactly, in an absolute Earth-centered reference frame. But these control points, you can only measure them up to 1 or 2 centimeter of accuracy, right? That's GNSS plus RTK. That's kind of a fundamental limitation of a technology, and I don't think they are systems that can have 1 millimeter of accuracy. Then, of course, there's the error that propagates from measuring the control points to observing it in Aria data, and that adds even more error. So it's really difficult to go down to an even higher accuracy.
In a way, then it's kind of Aria might be more precise, but we can't measure it. That's what you're kind of saying.
Well, we can definitely, with the early results we've had, we can clearly measure errors in the Aria SLAM system, because at 2 kilometers of trajectory, you start seeing clearly visible errors that are much larger than a few centimeters.
Okay, cool.
So it's all about the scale, essentially.
Mm-hmm. Cool, thank you.
Cool, awesome, thanks. Thank you.
Thanks, Paul-Edouard.
Thank you.
All right, well, that brings us to the end of today. And actually, 1 second, I'm just going to close with a couple of slides to leave you with. I know that was a ton of information that you consumed over the last 4 hours. Seeing presentations from us, from researchers, both internal to Meta and from our partners. And I just want to leave you with a few summarizing thoughts. So I just want to recall that AI is only as good as its training data and its context. And we're really working on providing the appropriate context for being able to create AI systems that can be most helpful to us. And I just want you to take away that there's both the Aria Research Kit, which is both the device and the full set of tools that you need to work with Aria. And then if you want to get started right away, the Open Science Initiatives is composed of our datasets, models, and challenges. It's the lowest lift for getting started. And this is the Aria Research Kit website again. I encourage you, if you have ideas of how to use Aria for your research, go online and make an application, and we'll be very happy to talk to you and review it. Also, if you're interested in our datasets, you can go here. And I think the last thing that I want to say also is that we will have a booth for the entire conference. So come to our booth, come talk to our experts. If you have ideas, we're happy to brainstorm with you. And then we'll also have the streaming demo there, and you can try it on. You can see what Aria is like to wear, and we're really excited to have you come by. Thanks for your time today.